Can you learn calculus in the time it takes to watch a long movie? Yes, you can. My name is Dennis Davis. I'm an engineer, not a mathematician. I try to make my videos visually enlightening and fast-paced. But this video is very long because it covers almost the entire first year of calculus using visuals, graphs, and diagrams. I'd rather show you calculus visually than just tell you the rules and formulas. If you see where the rules and formulas come from, that can help you understand, remember, and make use of them. To become truly proficient at calculus, you'll need practice, which you won't get just by watching this video. In the description, I'll link to some helpful practice-oriented videos by others. Whether you're new to calculus, studying it now, or just want a refresher, I hope you'll find this video informative and engaging. My only assumptions are that you're already familiar with functions and algebra. So here we go. Calculus is the study of change and rates of change of mathematical functions. When we use calculus, we perform operations on functions that result in different functions. This isn't a new idea at all. We perform operations, such as addition, on numbers to get new numbers. We operate on sets to get new sets, on matrices to get new matrices, and we can operate on functions to get new functions. In fact, you've probably already done this in algebra when you had a function and found its inverse. We start with a function, f of x, and write out f in terms of x and y, so that y equals some function of x. Then we rewrite the equation switching x and y. Then solve the second equation for y, and that's the inverse of the first function. So we start with a function, perform an operation on it, and get a new function. The point is, taking an existing function and performing some operation on it to get a new function isn't a new or advanced math concept, and that's really what calculus is. In fact, calculus is all about performing two operations on functions. That's it. That's calculus. The first operation is called differentiation. When we differentiate a function, the new resulting function is called the derivative of the first function. The derivative is the first topic we'll cover. Learning to take the derivative of a wide variety of function types is roughly the first semester of calculus. The second calculus operation is called integration. When we integrate a function, the new resulting function is called the integral of the first function. Integration is roughly the second semester of calculus. And there's a wonderful relationship between these two operations that we'll get to at just the right time. When functions are simple, these operations are simple, and calculus is simple. It's when the functions we operate on get complex that calculus seems complex. So if calculus has a reputation for being a difficult subject, it's not really calculus's fault. We'll start with the derivative and consider a simple function. F of x equals x minus 1. This is a linear function, so its graph is a straight line. I said calculus was the study of change and rates of change, and the rate of change of a straight line is its slope, rise over run, delta y over delta x. I like to color code things in my videos. I'm using blue for x coordinates and distances, and yellow for y. And I'll use pink for slope or rates of change. I won't draw a lot of attention to the colors and may not mention them again, but their consistent use may let you see some apparent order or pattern that might not otherwise be clear. For a straight line, it's easy to find the slope. Just pick any 2 points and subtract their y and x coordinates to get delta y over delta x. Delta y is 3 minus 0, this distance, the difference between the yellow y coordinates. And delta x is 4 minus 1, this distance, the difference between the blue x coordinates. So for this linear function, the slope is 3 over 3, or positive 1. For every unit x changes, y changes by 1 times that amount, since the slope is 1. If the slope were positive 1/2, then when x changes by some amount, y changes by positive 1/2 as much. If the slope were negative 2, Then when x changes, y changes by negative 2 times as much. That is, 2 times as much, but in the opposite direction. Y would get smaller as x gets larger. When the graphed line is horizontal, the slope is 0 because y never changes, so delta y is 0. When the graphed line is vertical, the slope is undefined because x never changes. Delta x is 0, so delta y over delta x is undefined, since the denominator is 0. Everything's nice and simple when the function is linear, but what about the function f of x equals x squared minus 2x plus 1? The graph of this function is a parabola, so now the question, what's the slope, prompts a new question in response. Where do you mean? Because the slope is smoothly changing, it's different at different points. Suppose we wanted to find the slope of the function at x equals 1.6, here. Now, if you know calculus, or more specifically the rules of differentiation that we'll cover soon, then within a few seconds you can figure out that the slope at x equals 1.6 is 1.2. If you don't know calculus yet, I promise that soon you'll know how to do this. But without calculus, it's not easy. After all, slope is rise over run, delta y over delta x. But with just 1 point, where does delta y come from? Or delta x? Slope is the rate of change, and there's no change at a single point. There's only a change between 2 points. So it's a tricky question. We could eyeball it by drawing our best attempt at a line tangent to the curve at x equals 1.6, then measure the slope. It won't be very accurate. It's not always easy to draw an accurate tangent line, but without calculus, that might be an option. But let me show another way. In the 1600s, the great minds that developed calculus approached the problem this way. I'll zoom in on our grid at the red point of interest where x equals 1.6. We want to know the slope at the red point. I warned you I like to color code things. Let's choose a nearby point, green, and find the slope, delta y over delta x, between red and green. So we estimate the slope at red as the slope of the pink line between red and green, delta y over delta x. It'll be pretty close, and the closer green is to red, the better the estimate. This is the approach that will lead us to the derivative. The x value of our red point, where we want to know the slope, is 1.6. We find the y value by plugging 1.6 into the function, and we get 0.36. Let's choose a nearby x value for the green point. Let's say 1.601. So we find the y value for the nearby green point by plugging 1.601 into our function to get 0.361201. Remember, here's our function, y equals x squared minus 2x plus 1. We can easily find the slope delta y over delta x between 2 points given their coordinates. And we get 1.201, the slope between red and green, which is our estimate for the slope at red. Calculus will tell us, I promise, that the slope at red is 1.2, so our estimate is very close. The closer we let green get to red, the closer the estimate will get to 1.2. So let's prove it. We'll still choose a nearby green point, but now, instead of choosing an actual small distance away from red, such as 0.001 or 0.0001, we'll use a variable for the tiny x distance to green and call it h. The coordinates of the red point are still 1.6, 0.36, but let's consider the coordinates of the green point. Its x-coordinate is 1.6 plus h, and its y-coordinate is the function's value when we plug in 1.6 plus h for x. Now let's find the slope as delta y over delta x. Delta y is the y-coordinate of the green point, f of 1.6 plus h, minus the y-coordinate of the red point, which is still 0.36. I'm shading the components to the color of the corresponding point, and delta x is the x-coordinate at green, 1.6 plus h, minus the x-coordinate at red, 1.6. The denominator, delta x, looks pretty easy to simplify. 1.6 plus h minus 1.6 is simply h. This makes sense. We chose h over here to be delta x. So to find delta y over delta x, we'll need to expand this expression by taking our function f of x and rewriting it, substituting 1.6 plus h in for x. This is just algebra, so I'm showing it quickly. Pause if you want to step through the details. We end up with this expression for the y value of the nearby green point. So we can now find delta y over delta x, 0.36 plus 1.2h plus h squared minus 0.36 all over h. The plus 0.36 and minus 0.36 cancel, leaving us with 1.2h plus h squared over h. As long as h is not 0, which it's not, it's some tiny change, but not 0, then we can cancel an h from each term, and the slope delta y over delta x is 1.2 plus h. Let's remember that we said h was an arbitrarily small number. We're going to find the limit of delta y over delta x as h approaches 0. You may be familiar with the concept of the limit from studying discontinuous functions in algebra. We write the limit like this: LIM, and underneath a variable, right arrow, and a literal value. We read this as the limit as h approaches 0. In our case, the limit of 1.2 plus h as h approaches 0. As h gets closer and closer to 0, the expression 1.2 plus h gets closer and closer to 1.2. So the limit is 1.2, and that's delta y over delta x, the slope at the red point, or at least the slope as delta x, we called it h, approaches 0. And now we can continue our dialogue. What's the slope? Where do you mean? At x equals 1.6. The slope there is 1.2, that we found by taking the slope between two very close points at the limit as the difference between their x-coordinates approach 0. I want to review this equation again, which is how we estimate the slope of a function at a point using algebra. You'll see this important expression in the first chapter of every single calculus textbook. We're going to use it several more times, and I want to make sure you're comfortable with it. It's the algebra behind estimating the slope at the red point as the slope between the red point and the nearby green point, delta y over delta x. The difference between the y-coordinates is delta y, the numerator of our slope estimate. The difference between the x-coordinates is delta x, the denominator of our slope estimate. We just need to come up with expressions for these differences. The x-coordinate of the red point is simply x. So the red y-coordinate is the function's value at x, f of x. The x-coordinate of the nearby green point is x plus h. H is the small delta x amount we added to x to get a nearby point. So the green y-coordinate is the function's value at x plus h, f of x plus h. So for the numerator, we can plug in the difference, f of x plus h minus f of x. I can include the green and red memory aid, y-coordinate of green minus y-coordinate of red. For the denominator, we get x plus h minus x, green x-coordinate minus red x-coordinate. Well, it doesn't get written out this way very often since x plus h minus x so obviously simplifies to h, and h is the small distance we deliberately chose for delta x in the first place, so the denominator is usually just h, same thing. So when you see this expression, please think of this triangle and the rise over run slope it represents, delta y over delta x. 2 quick points. First, I'm illustrating a positive slope, but if the slope were negative, the expression will correctly result in a negative estimate for the slope, since f of x is greater than f of x plus h. Subtracting a larger number from a smaller will result in a negative number. H is always positive since it's the small delta x we added to x, so the equation works for positive and negative slopes. The second point is the key idea that uses this expression as the entryway into calculus. Let me make a copy of the diagram and expression. The top and bottom start out identical, but I'm going to make changes to the bottom to transform it, step by step, into the key foundation of calculus. We used the limit a moment ago to find that the slope of our function was 1.2. When we take the limit as delta x approaches 0, something very special happens. First, the nearby green point approaches the red point. That's pretty obvious since h is the distance between their x-coordinates and it's approaching 0. Second, the expression is no longer an estimate of the slope, it is the slope, or what we call the derivative. So let me change the header. The expression at the limit isn't the algebraic estimate of the slope, it's the algebraic definition of the derivative. And there's one more important change. At the limit, delta y and delta x get new names and symbols. They're called dy and dx. The d stands for differential. We'll talk more about it soon. On the top is the estimated slope of a curve based on nearby points. On the bottom is the definition of the derivative at the limit as the horizontal distance between the 2 points approaches 0. So here's how we use the limit to find the derivative at 1.6. There was a lot of algebra involved to get to our answer, 1.2, but no calculus, yet. You might not believe me, but you will soon. Calculus is easier than taking limits. Taking limits with algebra is tedious. This is tedious. Certainly not difficult, but time-consuming and prone to errors if you're not careful. And when I promised to show you how you could know almost immediately that the slope at 1.6 was 1.2, I was not talking about doing all this algebra in your head. Calculus is easier than this, and I'll show you there's just one more key step. The destination will make the journey worth it. So we just found the slope of the function at x equals 1.6 by plugging 1.6 into the function and finding the slope to a nearby green point. Now let's see what happens when we generalize. We'll algebraically evaluate delta y over delta x at the variable value x instead of the specific value 1.6. The delta y over delta x formula has the same parts. The y-coordinate of the nearby green point is f of x plus h. The y-coordinate of the red point is f of x. The x-coordinate of the green point is x plus h, and the x-coordinate of the red point is x. The denominator, of course, simplifies to h. So when we expand f of x plus h, we get x plus h squared minus 2 times x plus h plus 1. And you can see the correspondence to the terms in the function. We just plug in x plus h for x, expand, and simplify using algebra. So here's the x-coordinate of the green point in terms of x. It's the first term in the numerator of our delta y over delta x slope expression. Next, we need to subtract f of x, which is right here, minus f of x. Three terms cancel, and we're left with these terms as delta y, h squared plus 2xh minus 2h. The denominator is h, the arbitrarily small number we chose for delta x. We cancel an h from each term and get delta y over delta x equals h plus 2x minus 2. Let's take the limit as h approaches 0. We get 2x minus 2. Now, let's pause for a moment and appreciate what we've just done. We have an expression for the slope of the function y equals x squared minus 2x plus 1 in terms of x. Have we just found a function that returns the slope of another function? Let's call the second function f prime of x and try it out. More on this prime notation shortly. A moment ago, we found that the slope at x equals 1.6 is 1.2. So let's try out our new general function f prime of x at 1.6. We get 2 times 1.6 minus 2. 3.2 minus 2. Yes, we get 1.2, just like before. Let's try this point. At the vertex of the parabola, where x equals 1, it looks like the slope we get should be 0. f prime of 1 equals 2 times 1 minus 2. Yes, it's 0. And we have indeed found the function f prime of x that returns the slope of f of x for any value of x. And now we can finish our dialogue with the broader question. What's the slope of this function at any x? And the answer for this function is 2x minus 2, because this will return the slope of x squared minus 2x plus 1 for any x. So we've just performed the first calculus operation, differentiation. We started with a function, f of x equals x squared minus 2x plus 1, and we performed an operation on it to yield a new function, the first function's derivative, f prime of x equals 2x minus 2. The derivative of a function evaluates to the slope of that function at every x value. We found the derivative the hard way, by taking limits and crunching through algebra. I'll show a simpler way in a moment, but regardless of the method, we've just performed the differentiation operation to get the derivative of a function. Since the derivative of a function is just another function, we can graph it also. The pink line is f prime of x equals 2x minus 2. F prime of x is a common notation for the derivative of f of x. I'll cover some notation conventions in a moment. The pink line represents the derivative of the white parabola. So of course the derivative's value at x equals 1.6 is 1.2. The slope of the parabola at x equals 1.6. Let's go over some vocabulary and notation concerning derivatives. With slopes, we quite naturally speak of delta y over delta x, the slope between 2 points. This ratio gets closer and closer to the slope at x as delta x gets closer and closer to 0. In calculus, we introduced new terms for delta x and delta y that have the limit as delta x approaches 0 concept built in. We say that the limit as delta x approaches 0 of delta x is dx. We use lowercase d instead of the Greek letter delta as calculus shorthand that means at the limit. So when you see d, it means at the limit as the change to the independent variable, often x, approaches 0. One more time, instead of writing all this, you can just write this, which means the same thing. It's common to think of dx as the slightest, tiniest change in x, and this thought might serve you well, but dx is really whatever delta x becomes as it gets closer and closer to 0. It's an idea that we treat like a number. dx is called the differential of x. I'll have to draw it with some sort of thickness so we can see it, but it's actually unimaginably narrow. dy is the differential of y, which is delta y at the limit. But it's not the limit as delta y approaches 0. Like dx, it's also the limit as delta x approaches 0. dy is the interesting thing we observe as delta x gets closer and closer to 0. So at the limit as delta x approaches 0, our ratio, delta y over delta x, becomes dy over dx. This is the derivative. The ratio dy divided by dx is the differential of y with respect to x. It's often said out loud as dy by dx or simply dy dx. Let me show you some other ways you might see the derivative represented. This notation denotes a differential change in something with respect to x. We can pull the something out of the ratio, it means the same thing. This part means the change or derivative with respect to x, and this part is what we're taking the derivative of. Since y equals f of x, we could also write d by dx of f of x. It means the same thing. And since f of x equals x squared minus 2x plus 1, we could also write d by dx of x squared minus 2x plus 1. They all mean the same thing. Hopefully the symbology is clear. Differential of something with respect to the corresponding differential of x. I mentioned this one earlier, but derivatives of functions can also be represented with the prime or single quote character. F prime of x is the derivative of f of x. So these are all different representations of the same calculus concept, the derivative of f of x with respect to x. We've been using x and y as our independent and dependent variables, which is quite natural considering these are the standard Cartesian coordinate system variables. And we often represent the dependent variable y as a function of the independent variable x, like this. But you should know that other variables can be used. For example, in physics and engineering, the independent variable is often time, if the function we're operating on represents something that can change over time. For example, s equals f of t could represent the displacement of a particle from a starting point at time t. In this case, the derivative of the function is ds by dt, not dy by dx. I just don't want you to get locked into x and y and not recognize calculus concepts when you see them referencing different variables. As it happens, the independent variable t for time is so common that there's an additional shorthand representation for the derivative of a function with respect to time, f dot. A function label with a dot over it represents the derivative of that function with respect to time. Now let's go over the basic rules of differentiation, which are rules and techniques to find the derivative of various types of functions. And the big payoff is that the rules will let us find the derivatives without the time-consuming process of taking limits. Covering the rules of differentiation will take some time, as this is essentially the entire first semester of calculus, and I'm going to take limits to show you that the rules are true and correct and give you insight into why they work. On the left are 5 types of functions. Each rule is a special shortcut for taking the derivative of that function type. The shortcuts are a result of observing the pattern that reveals itself when we take the limit. You'll see what I mean. On the right side are the rules or shortcuts for how to find the derivatives of combinations of function types on the left. So that you don't give up hope, let me tell you exactly what we'll be doing. I'll start with these 4 rules on the top. Then I'll show you some super shortcuts involving these 4 rules. At this point, I'll keep my promise because you'll be able to differentiate x squared minus 2x plus 1 almost instantly in your head. And you'll note that the derivative at x equals 1.6 is 1.2. By this time, we'll know enough calculus to set up and solve some interesting problems. Then I'll introduce the second derivative and higher order derivatives, and then we'll finish the rules of differentiation with these last 5 rules. I'll show this agenda again so we can keep track of our progress. Covering these topics, we'll finish the first calculus operation, differentiation. After that, we'll learn the second calculus operation, integration. So, let's dive in. We'll start with the derivative of a constant. If we have a function f of x equals a constant, such as 3, its graph would be a horizontal line. I'm going to make constants green. No matter what value we choose for x on the horizontal axis, the function returns 3, and the slope is 0. This is true for any constant c. Since there's no change to the function's value as x changes, the derivative is 0. We write the generalization like this: d by dx of c equals 0, where c is any constant. It says that the derivative of a constant is 0, and that's the constant rule. We're not cheating or saying anything new. If we were to again let 2 points get closer and closer to each other and apply the limit to the slope expression, we would get 0. We'd get 0 every time because we'd always get c minus c here. All of these rules of differentiation are generalizations of what happens to the slope as we take the limit. We simply notice the pattern, like we did here for constants, and then use the pattern instead of taking limits. And that's why calculus, at least differentiation, is easier than algebra. The next pattern, or rule of differentiation, is called the power rule. Heads up, the power rule is a big part of how you can take the derivative of x squared minus 2x plus 1 in your head. I'll show the rule with some examples, then I'll show how it can be visualized. I'll tell you the power rule first, then I'll prove it's true in a few minutes. The power rule is applied to powers of x, like x squared, x cubed, x to the fourth, and so on. It says that the derivative of x to the n is n times x to the n minus 1. It looks horrible, but every calculus student in history just remembers this about the power rule. Bring the exponent downstairs and subtract 1. So to find the derivative of x cubed, we take the exponent, 3, and bring it downstairs in front of x. Then we subtract 1 from the exponent and get 3x squared. Can you see how that matches the power rule shortcut? What's the derivative of x squared? Well, we bring the 2 downstairs to get 2x to the something. For the exponent, we subtract 1 from the original exponent 2. 2 minus 1 is 1, and x to the power of 1 is just x. So the derivative of x squared is 2x. Can you see on your own that the derivative of x to the fourth is 4x cubed? Yes, the power rule is pretty easy. I'm arranging the exponents in numerical order, so let's go back up top for the derivative of x to the first power. Bring the 1 downstairs and the exponent becomes 0. Since x to the 0 is 1, the derivative is 1 times 1, which is 1. So the derivative of x is 1. This one's easy to see on a graph. The line representing y equals x is a straight line, whose slope is obviously 1. It all works out. Let me scooch over here to get more room. I'll sketch in x to the 0 and x to the first power so you can see that the pattern is kept. And speaking of pattern, let's go up top again to find the derivative of x to the 0. The 0 comes downstairs and the exponent becomes negative 1. Well, 0 times anything is 0, so the derivative is 0. And let's notice that x to the 0 power is 1. So this is a special case of the constant rule, which is that the derivative of any constant, such as 1, is 0. So the power rule and constant rule give us the same derivative for exponent 0. Pretty neat, it all works together and the rules are consistent. How about this one? What's the derivative of the square root of x? Well, remember that the square root of x is x raised to the 1/2 power. The power rule isn't limited to integer exponents. We bring the 1/2 downstairs and subtract 1 from 1/2 to get an exponent of negative 1/2. Since x to the negative 1/2 is 1 over square root of x, this gives us 1/2 times 1 over the square root of x, or 1 over 2 square root of x. The fraction has a radical in the denominator, so we can rationalize by multiplying the numerator and denominator by square root of x to get square root of x over 2x. And that's the derivative of the square root of x using the power rule, which works for all real exponents, not just integers. Well, I've told you the power rule, but I haven't proven that it's true. Now I'll prove it with limits. Let's take the derivative of x to the n as the limit of delta y over delta x like this, as h approaches 0. Just like before, we have our green and red y values. The most tedious part of this proof is expanding the green binomial. In this video's description, I put some links to videos that go into more detail on the binomial expansion. In short, when the green x plus h to the n is expanded, the first green term will always be x to the n, and the last green term will always be h to the n. Then, moving towards the middle, the second term is x to the n minus 1 and h to the first, prefixed with the binomial coefficient, which for the second term is always n. None of the other coefficients are important for this proof, but it's interesting how the coefficients of each green term follow a pattern revealed by Pascal's triangle. But that's not what this video is about, so see the links in the description for more information. Math is so interesting and easy when you can see how it all fits together. The second to last green term will always have x and h to the n minus 1, along with the binomial coefficient, which is also n for the second to last term. All the terms in the middle, denoted by the orange box, are the remaining binomial expansion terms, and will have factors of h to a power of 2 or greater. That will be important for our proof in a moment. In fact, all the green terms, except the first two, will have h factors raised to a power of 2 or more. And there's still the red x to the n term we subtract at the end. Let's bring everything down and encapsulate the orange. We'll always have positive and negative x to the n, so they'll cancel every time. Every remaining term will always have at least one h. Since the denominator is h, we can cancel an h from each remaining term. This leaves n times x to the n minus 1 plus the orange terms, which initially all had factors of h squared or higher, and now, since we divided through by h, they all have factors of h or higher. When we take the limit as h approaches 0, all of these terms approach 0, and we're left with n times x to the n minus 1. And so we've proven the power rule. Once more, the rule comes from the slope expression and is the pattern we notice every time we take the limit. So when we do calculus, we don't need to take the limit, we just use the pattern. And the pattern for the derivative of x to the n is n times x to the n minus 1. Let me show you a visual interpretation of the power rule that should build your intuition. The power rule tells us that the derivative of x squared is 2x. Let's consider the function x squared to be the area a of an actual square with sides of length x. The derivative of x squared with respect to x is the amount the area changes per change in x. So if we let x change by this differential amount, dx, by how much does the area of the square change? Well, it changes by the area of these two narrow strips. This one has an area of its height, x, times its width, dx, so x dx. This one on top also has an area of its height, dx, times its width, x, so its area is also x dx. For the sake of completeness, let me point out this tiny corner piece whose area is dx squared. It's one of the orange terms from the binomial expansion that goes to 0 as delta x approaches 0. So at the limit as delta x approaches 0, the change in the blue square's area, the differential of a, is the differential of our function x squared. This is the added area to x dx. So the derivative of x squared, the change in x squared per change in x, is indeed 2x. Let's look at the derivative of x cubed visually. The power rule tells us that its derivative is 3x squared. Let's visualize the function x cubed as the volume of an actual cube whose sides have length x. When we increase x by the tiny differential dx, what happens to the volume of the cube? When we add dx over here, we get this new volume, a thin slab on this face, whose volume is the area of the face, x squared, times its thickness, dx. So the additional volume is x squared dx. You might see where we're going. We get the same additional volume on these other two faces for a total of 3, x squared dx. Because I've drawn dx with some visible thickness, you might notice these three thin regions having volume x, their length, times dx squared, their cross-sectional area. So their added volume is 3x dx squared. This last tiny volume has sides equal to dx, so its volume is dx cubed. These orange terms all go to 0 at the limit, but it's interesting to see that even they have a visual interpretation on the diagram. So the differential change in the volume x cubed is 3x squared dx. This means the derivative of x cubed is the change in x cubed per change in x, which is indeed 3x squared, as the power rule tells us. To illustrate the usefulness of the power rule, consider finding the derivative of x to the fourth with limits. As you can see, the power rule is so much simpler and always gives the same answer. Once more, when we do calculus, we use these shortcut rules. We don't take limits. In a calculus course or textbook, you'll take limits only for the first week or two to demonstrate what the derivative means. But once you learn the rules of differentiation, you'll use them, and you won't find limits anymore. But I will still find limits in this video to prove the rules and illustrate some points. Now, we'll go over ways to take the derivative of combinations of functions. The first is the addition rule. It says that the derivative of the sum of two functions is the sum of their distinct derivatives. Or, in terms easy to remember, the derivative of the sum is the sum of the derivatives. Here I'm using f and g as the two functions, and the prime symbol to denote their derivatives. An example should make this simple. Let's find the derivative of x squared plus x. First, the derivative of x squared is 2x, and the derivative of x is 1. So the derivative of x squared plus x is 2x plus 1. The derivative of the sum equals the sum of the derivatives. Let's look at the graph and see why this makes sense. Here are the two functions we're adding, y equals x squared in white and y equals x in green. And the blue curve is their sum, y equals x squared plus x. Let's take two nearby x values and look at the corresponding delta y's for the three curves. Here's delta y for white, the change in x squared over our small delta x. And here's delta y for green, the change in green y over our small delta x. And finally, here's delta y for blue, the change in x squared plus x over our small delta x. Can you see that since blue equals white plus green, that delta y for blue equals the sum of the white and green delta y's? Since blue equals white plus green everywhere, any difference in blue must be equal to the corresponding difference in white plus green. Remember, as delta x approaches 0, we use the word differential to describe the changes. So the differential of the sum equals the sum of the differentials, and that's the addition rule. Without elaboration, I'll assert that the same relationship holds with subtraction, that the derivative of the difference between two functions equals the difference of their respective derivatives. So I'll write the addition rule with plus or minus, since it works for addition and subtraction. Next is the product or multiplication rule. It says that the derivative of the product of two functions is the first function times the derivative of the second, plus the second times the derivative of the first. So the pattern is different than the addition rule, because the derivative of the product is not the product of the derivatives. Like we did for the power rule, let's visualize the product rule by considering the product of the two functions to be a rectangle whose area is the product, f times g. On this graph, the axes represent the values of the functions, not the independent variable x, at least not directly. When we increment x by its differential dx, f of x increases by its own derivative, df by dx, and the area of the rectangle increases slightly by this thin strip. At the same time, g of x increases by its own different derivative, dg by dx, and the area of the rectangle increases slightly by this thin strip. The area of this first strip is its height, g of x, times its width, df by dx. And the area of the second strip is its height, dg by dx, times its width, f of x. So the derivative of the product of the two functions is the additional area of the two rectangular strips, and their dimensions are each function times the derivative of the other, and that's a nice visual interpretation of the product rule. Now we can look back at our sample function x squared minus 2x plus 1 and consider which of these rules we'll need to use to find its derivative. Well, it's the sum of three simpler functions, so let's start with the addition rule. The derivative of x squared is 2x by the power rule. For the next term, we need to subtract the derivative of 2x, which is the product of 2 and x. So we'll need the product rule. We'll get back to it in a second. And the derivative of 1 is 0 by the constant rule. Interesting, to take the derivative of a simple polynomial, we need all four of the rules we've covered so far. Now, let's use the product rule to find the derivative of 2x. The product rule says that the derivative of the product is the first function times the derivative of the second, plus the second function times the derivative of the first. The first function is 2, and the second function is x. The derivative of 2x is 2 times the derivative of x, plus x times the derivative of 2. The derivative of x with respect to x is 1 by the power rule, so the first term becomes 2 times 1. The derivative of 2, a constant, is 0, so the second term becomes x times 0. This all simplifies to 2, so the derivative of 2x is 2, which makes the derivative of our original function, x squared minus 2x plus 1, equal 2x minus 2. Of course, this is the same answer we got when we took the limit. Well, This is the function I promised you'd be able to differentiate in a few seconds, but using these 4 rules certainly took more than a few seconds. Let me show you a calculus super shortcut based on the product rule. The derivative of any constant k times x with respect to x is simply the constant k, because when we use the product rule, we get k times the derivative of x plus x times the derivative of k. The derivative of x with respect to x is always 1, so the first term will always be k. And the derivative of k with respect to x is always 0 by the constant rule, so the second term will always be 0. This pattern occurs every time the product rule is applied to kx, so the derivative of any constant k times x is always k. This is the kind of pattern the rules of differentiation let us exploit. Now, let's go back and find the derivative of x squared minus 2x plus 1 at x equals 1.6 by differentiating left to right. 2x minus 2. With practice, you'll learn to ignore constants. Plug in the chosen x value of 1.6 to get 3.2 minus 2, so 1.2. And that's how, with practice, you can know almost immediately that the derivative or slope of x squared minus 2x plus 1 at x equals 1.6 is 1.2. Okay, now for another great shortcut, which is a generalization of the first one for kx. This time we'll take the derivative of kx to the n. So we have a power of x with some constant coefficient k. So this is the product of 2 functions, k and x to the n. Let's use the product rule again and see where this leads us. We have the first times the derivative of the second plus the second times the derivative of the first. The derivative of x to the n is straight from the power rule, n times x to the n minus 1. And the derivative of constant k is, of course, 0. So the second term becomes 0. This leaves the derivative as k times n x to the n minus 1. At first, this new shortcut looks a little cumbersome like the power rule did. But look at what it lets us do. When we bring the exponent downstairs, we can just multiply it by whatever coefficient is already there. So the derivative of 4x cubed is 12x squared. We bring the 3 downstairs, multiply it by the coefficient of 4 that's already there to get 12, and then we subtract 1 from the exponent. This simple super shortcut has the product rule, power rule, and constant rule built in. It automatically follows all the rules. So, knowing this super shortcut and using the addition rule, we can easily take the derivative of long polynomials. We just work left to right, differentiating one term at a time. Polynomials are incredibly simple to differentiate. I need to finish the rules of differentiation, but first we actually know enough calculus to solve some interesting problems known as optimization problems. They involve finding the local minimum and maximum values for a function. For example, suppose this curve represents the net profit our company would make by manufacturing and selling X number of a particular item. If we make and sell too few, our profit will be limited by the low number. If we make and sell too many, our supply might exceed the demand, and our extra cost for running more machines and hiring more people won't be offset by the higher volume. There's some independent variable here that will maximize the profit function. How do we find it? Let's notice that at the maximum, the slope of the function is 0. Lucky for us, we know calculus. We can take the derivative of the profit function and find the equation for its slope anywhere. When we set the derivative function equal to 0, we can solve for x to get the exact point at which the original function is at its maximum. Our profit function f of x in thousands of dollars is negative 0.012x squared plus 9.8x minus 1,500, where x is the number of units we manufacture and sell. To find the value for x that maximizes the function, we take the derivative of the function and set it equal to 0, and solve for x. We know how to take the derivative of polynomials. We have negative 0.024x plus 9.8. Set this equal to 0 and solve. X equals 408.3. So we should make 408 units to maximize our profit. If your problem statement asks you for the profit amount, plug 408 into the original profit function to get the maximum profit amount. F of 408 equals 500.8. And we're told this is in thousands of dollars, so the maximum profit is $500,800 when we make and sell 408 units. Let's do another problem. Suppose we have a rectangular sheet of metal that measures 32 centimeters by 24 centimeters. We want to make a box by cutting squares out of the corners and folding the resulting sides up. The box won't have a lid. The shapes we cut out of the corners need to be squares so that when we fold the sides up, they'll all have the same height. What are the dimensions of the box having the greatest volume, and what is the volume? Okay, we need to express the volume V as some function of a variable. Let's use the length of the square sides that we cut out of the corners and call it x. Of course, all of these distances are x. The volume of the box will be its width times its depth times its height. The width is this distance, which in centimeters is 32, minus 2x. The depth is 24, minus 2x. So when we multiply these expressions, that gives us 4x cubed minus 112x squared plus 768x. I'm skimming over the algebra so we can focus on the calculus. To find the x value that maximizes this function, we'll take the derivative, set it equal to 0, and solve for x. The derivative of the polynomial is 12x squared minus 224x plus 768. This is a quadratic equation, and there are several ways to solve it. I used, but won't show, the quadratic formula to get two possible solutions, x equals 14.1 centimeters and x equals 4.53 centimeters. We need to check these numbers for feasibility. The short side of the metal sheet is 24 centimeters, so we can't cut out squares greater than 12 centimeters. There's not enough metal on that edge. So that leaves 4.53 centimeters as our answer for x. But that's not the answer to our problem. We're asked for the dimensions that maximize the box's volume and for that maximum volume. So we plug in 4.53 centimeters for x into our width and depth formulas. We get a width of 22.94 centimeters and the depth of 14.94 centimeters. The third dimension, height, is our value for x, 4.53 centimeters. So multiplying these dimensions yields a volume of 1,552 cubic centimeters. Any other value for the square size x will result in a lower volume. Let's look at a different function. This curve has 2 points where the slope is 0, a local maximum here and a local minimum here. When we use the word local to describe a minimum or maximum, we mean compared to the points nearby. For example, the local maximum identified here isn't the function's maximum. It has higher values out to the right. And similarly, there are lower values closer to the y-axis than the local minimum identified here. Local means higher or lower than nearby points on either side. Anyway, when we set the derivative equal to 0 and solve for x, we get these x values. But it's important to be able to tell the difference between a minimum and a maximum. If our management team wanted to maximize profits and we recommended action corresponding to this point, that could be a disaster. Or if they wanted to minimize budget or time and we chose this point. Setting the derivative equal to 0 and solving for x will give us the points where the slope is 0, which could be a local maximum or minimum. But how can we know which? Let's color code the function's slope. Green for positive here to the left of the first 0 point. The slope is 0 at the maximum, of course, and then negative, red, between the two 0 points. Then the slope is 0 again at the minimum, and positive beyond the second 0 point. So the slope changes signs at the minima and maxima. This makes sense. If it's 0 at a point, it must be passing from positive to negative, or from negative to positive. But notice that at the maximum point, the slope is changing from positive to negative. And at the minimum point, the slope is changing from negative to positive. Let's plot the function's derivative. Of course, it's 0 at the 2 points where the function's slope is 0. At the local maxima, the slope of the pink derivative will always be changing from positive to negative, which means its slope is negative, as you can see here. And at local minima, the slope of the pink derivative will always be changing from negative to positive, which means its slope is positive, as you can see here. The slope of the derivative is positive at local minima. So what do we mean by the slope of the derivative? Remember, in calculus, we're just performing operations on functions that result in different functions. When we differentiate a function f of x to get its derivative f prime of x is just a new function that we can, in turn, differentiate to get its derivative. The derivative of a derivative is called the second derivative, or, depending on the variables, the second derivative of y with respect to x. I'll show more notation in a moment, but f double prime of x is a common way to denote the second derivative. The second derivative of a function tells us the rate of change of the slope of that function, and as you might guess, the derivative of the original function is called the first derivative. Here are 6 examples of curves from various functions f of x. For this first one, the slope f prime of x is positive since the function's value is increasing. And since the rate of change of the increase is not changing, that is, it's a steady increase, the second derivative is 0. In this example, the first derivative, f prime of x, is again positive since the function value is increasing. And since the rate of increase is itself increasing, the second derivative is also positive. In this example, the slope is increasing, but it's changing from a steep, high slope to a shallow, low slope, so the second derivative is negative. Can you see how these two functions have different behaviors, even though they both have a positive slope? For one, the slope is increasing at an increasing rate. For the other, the slope is increasing, but at a decreasing rate. Down here, the slope f prime of x is negative, and since the slope is constant, the second derivative is 0. This function has a negative slope, but the slope is getting less and less negative, so the second derivative is increasing, positive. And this last curve also has a negative slope, and its slope is getting more and more negative, so the second derivative is decreasing, negative. Since the first derivative can be thought of as the rate of change, the second derivative is essentially the rate of change of the rate of change. The second derivative is useful because it helps describe the behavior of functions, and it's especially useful in minimization and maximization problems to distinguish between local minima and maxima. At points where f prime of x is 0, x represents a minimum point where the second derivative is positive, and x represents a maximum point where the second derivative is negative. Now for some second derivative notation. The derivative of the derivative is the second derivative, f double prime of x. Since the derivative is dy by dx, we can write the second derivative as d by dx of dy by dx. Let's move the function up to the numerator. Now what follows is symbolic shorthand, not true algebra. We take the d and dy at the top and combine them to get d squared y, because there's 2 d's and 1 y. And when we take the 2 dx's and combine them, we get dx squared. So the symbolic representation of the second derivative of y with respect to x is d squared y by dx squared. I'm not saying it makes pure algebraic sense. Maybe a mathematician can tell us in the comments if there's a deeper meaning behind the symbol. I'm just an engineer, and I don't know. There are higher order derivatives, of course. The derivative of a function's second derivative is the function's third derivative. It's easy to extend the d by dx pattern to see the third derivative as d cubed y by dx cubed. F triple prime is another representation of the third derivative. Please don't think that higher order derivatives are any more difficult or complicated than the first derivative. It's the same differentiation operation following the same rules of differentiation. Well, let's get back to the remaining rules of differentiation, but first let's check our progress. We've covered 4 important rules of differentiation: the constant rule, the power rule, the addition-subtraction rule, and the product rule. Then we covered some super shortcuts involving polynomials, solved 2 problems, and learned about the second and higher order derivatives. Now we'll cover the last 5 rules of differentiation in this order. First, sine and cosine. Here's a sine wave, the plot of y equals sine of theta. You don't need to be an expert at trigonometry to differentiate sine and cosine. But if anything I'm about to say seems unfamiliar, I have a YouTube trigonometry course if you want to brush up, linked in the description. Let's draw the sine function's derivative by plotting a few points and seeing what patterns arise. We'll start with the local minima and maxima. They're always easy to see. So the derivative will be 0 and intersect the theta axis at these blue points. At these points where the sine wave crosses the theta axis in an upwards direction, the slope is 1. Using the expression for the slope again, let me demonstrate quickly and without elaboration that delta y over delta theta, we've made theta our independent variable, not x, is very close to 1 when green delta theta is very close to 0. The slope at these points is 1, so we'll plot the blue derivative points here at y equals 1. The y-coordinate of each blue point represents the slope of the red sine curve at that value of theta. The slope at these points is -1, so the blue points go down here. We could plot more points, but let me jump to the answer and plot the derivative of sine theta. It's this smooth curve. If you're familiar with trigonometry, you'll recognize this curve as cosine theta. The derivative of sine theta is cosine theta. Pretty neat. Let me show you a proof. It assumes a little trigonometry knowledge, but I'll go quickly. We'll consider a unit circle and focus on the first quadrant. Let's put angle theta in standard position. Since we're on a unit circle, this yellow length, the radius of the circle, is 1. This horizontal length is cosine theta, and this vertical length is sine theta. It's this vertical red length we're interested in. As theta changes ever so slightly by d theta, what's the change to the red length, d sine theta? Let's find out. The pink arc has length theta, which seems strange because green theta represents an angle, the number of radians, and pink theta represents a distance, the number of radii. But since the radius of the circle is 1, the numbers for theta, green and pink, are the same. Let's see what happens near this point, and note that this segment of the circle's circumference is very nearly a straight line as our focus of attention gets smaller and smaller. The derivative of sine theta is how much this vertical distance changes as theta changes by the tiny differential of theta, d theta. And since pink theta and green theta have the same measurement, I'm going to make the d theta label green to match our formula. To find the change in sine theta, let's draw this right triangle, and we can see that red sine theta changes by this amount that we can call d sine theta. So in this small triangle, we have representations for d sine theta and d theta, which are the numerator and denominator of the derivative we're trying to find. Since the trig ratios are the ratios between the various sides of a right triangle, our derivative ratio is one of the 6 trig functions. This angle is congruent to theta. I'm telling you this without proof, and so d sine theta and d theta are the adjacent and hypotenuse of the small triangle respectively. And adjacent over hypotenuse corresponds to cosine, and so we've shown graphically that the derivative of sine is cosine. Be careful because the opposite is not true. The derivative of cosine is not sine. Since the blue cosine curve has the exact same shape as the sine curve, it seems reasonable to deduce that the derivative of cosine will also have this shape. And let's note that the cosine is out of phase with sine. To illustrate, I'll add theta axis markers at every pi over 2 radians. And we can see that the cosine curve, the derivative of sine, is always pi over 2 radians to the left of sine. This is easiest to see by comparing peak-to-peak points where the functions have their maximum values. Since the derivative of sine is out of phase to it by pi over 2, does it make sense that the derivative of cosine would be out of phase to it? Well, yes indeed, it actually is. But as you can see, we don't have a function with these peak values. But if we flip the sine curve by taking its negative, we get the curve we seek, and the derivative of cosine theta is indeed negative sine theta. So what's the derivative of negative sine theta? By looking at the curve, you may see what's coming next. The derivative of negative sine theta is negative cosine theta. And taking the derivative of negative cosine theta gets us back to sine theta. And this four-step cycle comprises the trig-related rules of differentiation. It might help to remember that the trig functions alternate, that is, taking the derivative of a sine yields a cosine, and vice versa. Then it's easy to remember that the derivative of sine keeps the sine. So the derivative of positive sine is positive cosine, keep the sine. And the derivative of negative sine theta is negative cosine theta. The derivative of sine keeps the sine. On the other hand, the derivative of a cosine function flips the sign. The derivative of positive cosine theta is negative sine theta, and the derivative of negative cosine theta is positive sine theta. As you may know, there are 4 more trig functions, but we'll have to skip them for now and cover their derivatives later. Let's test our knowledge. What's the derivative of x cubed times sine x? Well, we have the product of 2 differentiable functions we can call f and g, so we'll use the product rule. The derivative of the product equals the first times the derivative of the second, plus the second times the derivative of the first. So it's simple. There's really no intermediary steps. Just write down the components, and that's the derivative of the product. X cubed cosine x plus sine x times 3x squared. Now for the chain rule. The chain rule is how we differentiate composite functions. A composite function is a function whose argument includes another function. You can think of composite functions as embedded functions, where one function is embedded in the other. For example, sine 2x is a composite function because sine is a function and its argument, 2x, is another function. The 2x function is embedded in the sine function as its argument. This is very common in math, science, and engineering, so you'll use the chain rule a lot, probably more than any other rule. Let's see why we need the chain rule when we find the derivative of sine 2x. First, we know the derivative of sine x with respect to x is cosine x. It's true, it's one of our rules of differentiation, the one we just covered. But we cannot say that the derivative of sine 2x with respect to x is cosine 2x. That's false. It's close. We'll need to adjust a bit with the chain rule to get the derivative of sine 2x, but this isn't right. Here's the pattern. The derivative of sine something with respect to that something equals cosine of that something. All 3 terms need to match for the differentiation rule to apply. And when we try to apply the rule to sine 2x, you can see that they don't match. I'm illustrating this with the trig rule, but the pattern applies to all the rules. If we were to modify the equation to be the derivative of sine 2x with respect to 2x, then the derivative would be cosine 2x, because all the terms would match. But in calculus, we're not asked very often to find the derivative with respect to a function of x, just with respect to x. So we need to dig a little deeper to differentiate composite functions. We can write composite functions like this, f of g of x. G is called the inner function because it's inside the argument for function f, which is the outer function. The derivative we're seeking is df by dx, the derivative of the outer function with respect to the argument of the inner function, our independent variable x. Here's the key to understanding the chain rule. A differential change in x will result in a differential change to g, dg by dx. That differential change to g, in turn, causes a differential change to f, df by dg. And that change to function f, df, that occurs as a result of the differential change to x, dx, is the derivative we want, df by dx. This is where the chain rule gets its name. The differential change to x ripples out in a chain reaction to cause the differential change in the outermost function. Here's the chain rule for differentiation. The derivative of f of g of x equals the derivative of f with respect to g times the derivative of g with respect to x. It should look familiar. It's the chain reaction we just traced from the independent variable x out to the outermost function. And it makes sense algebraically because there's a clear cancellation chain that makes the chain rule a lot easier to visualize and understand. So let's find the derivative of sine 2x. For the first factor, df by dg, we need the derivative of the outer, sine 2x, with respect to the inner, 2x. Let's notice that these terms match. You'll always get a match like this when you use the chain rule. We can use the trig rule that the derivative is cosine of the matching term. So df by dg equals cosine 2x. By the way, this is the answer we said was not right a moment ago. To get the correct answer, we need to multiply by the last term, dg by dx. G is 2x, so we get the derivative of 2x with respect to x. It doesn't get much easier than this. We have a super shortcut that tells us the derivative of 2x with respect to x is 2. So we use the chain rule to determine that the derivative of sine 2x is 2 cosine 2x. Let's do another problem and find the derivative of the square root of 5x squared plus 3. The inner function is 5x squared plus 3. The outer function is the square root. Let's rewrite the expression using an exponent of 1/2 to represent the square root. This should make it clear which function is the inner function and which is the outer. The first factor we need to find is df by dg, the derivative of the outer function with respect to the inner. The outer function is 5x squared plus 3 to the 1/2. The inner function is 5x squared plus 3. When you use the chain rule, you'll always have matching terms and can use the appropriate rule of differentiation. In this case, the power rule with the exponent 1/2. With the power rule, we bring the exponent downstairs and subtract 1 from it. We get 1/2 times the matching expression, which turns out to be the inner function g, raised to the negative 1/2. And that's the first term in the chain rule, df by dg. The second factor, dg by dx, is simple too. It's the derivative with respect to x of 5x squared plus 3. We use the power rule again for this one, 10x. You can simplify the expression using algebra, and we found the derivative of this composite function. Let's do one more chain rule example, this time with a composite of 3 functions. So we want to find the derivative of f of g of h of x. Let's set up the chain. The derivative of f with respect to g times the derivative of g with respect to h times the derivative of h with respect to x. 3 functions makes the chain concept even more obvious. Algebraically, the dg's cancel and the dh's cancel, leaving us with df by dx, the derivative of the outermost function with respect to the independent variable x. So let's find the derivative with respect to x of cosine squared, 4x. Let's rewrite the function as cosine of 4x squared, because cosine squared argument means the cosine of the argument squared. The inner function is 4x, the middle function is cosine, and the outer function is power of 2. Let me expand the derivative chain and show you again how simple this is. The chain always starts with the differential of the given outermost function as the numerator of the first factor. For this problem, the given function is cosine of 4x squared. So d cosine 4x quantity squared. The denominator of the first factor is dg, the differential of the middle function, which is cosine, so d cosine 4x. As usual, when we use the chain rule, we have matching terms, and the derivative with respect to something of something squared is 2 of that something. So the first term in the chain, df by dg, is 2 cosine 4x. The numerator of the second factor is the denominator of the first. That's how the chain works, d cosine 4x. The denominator of the second factor is dh, the differential of the inner function, which is 4x, so d 4x. Again, our terms match, and we have the derivative of cosine of something with respect to that something. The something is 4x, and the derivative of cosine is negative sine. So the second term, dg by dh, is negative sine 4x. Following the pattern, the numerator of the third factor is the denominator of the second, differential of 4x. And finally, at the end of the chain is the differential of the independent variable x, dx. The last factor will be a straightforward derivative. The derivative of 4x with respect to x is 4. So the last factor, dh by dx, is 4. Rearrange the terms if you like, and we found the derivative of cosine squared 4x. And that's the chain rule, the one you'll use most often in real life, and very easy with practice. Next is the quotient rule, where we'll find the derivative of one function divided by another. Put differently, we're finding how the ratio between two functions of x changes as x changes. First, the derivative of the ratio is not the ratio of the derivatives. That might remind you of the product rule, since the derivative of the product is not the product of the derivatives. The quotient rule says that the derivative of the ratio is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. We can prove it's true using the product rule and chain rule. First, we rewrite the quotient as a product with the denominator raised to the negative 1 power. So we have d by dx of f of x times g of x to the negative 1. So we use the product rule, the first times the derivative of the second, plus the second times the derivative of the first. The derivative has 4 components, each straightforward, except this one is a composite of a function raised to a power, so we'll just need to apply the chain rule. We have the derivative of some function raised to the negative 1, so the power rule tells us that's negative 1 times the function raised to the negative 2. Then, to finish the chain rule, we multiply by the derivative of the function, g prime of x. Now let's simplify. On the left side, we have negative f of x times g prime of x all over g of x squared. Then we add the right side, f prime of x over g of x. So we're adding two fractions, but their denominators don't match. If the denominators matched, we could add their numerators. If we multiplied the right denominator by g of x, then they'd both be g squared of x. So let's multiply the right term by g of x over g of x. And that's it. If we swap the left and right terms, the format will match the quotient rule stated above. So we've derived the quotient rule from the product rule and chain rule. To remember the chain rule, I start with the denominator squared. Then the numerator expression starts with the denominator not squared. Then, like the product rule, we multiply one by the derivative of the other. But unlike the product rule, we subtract instead of add. Then the right term is opposite, derivative-wise, from the left term. F prime becomes f, and g becomes g prime. Write it from scratch a few times, and you'll know it. Let's find the derivative of a quotient, 3x cubed minus x squared plus 2 divided by cosine x. We'll start with the denominator squared, cosine squared of x. Then for the numerator expression, we start with the denominator again, not squared, cosine x. Then multiply by the derivative of the numerator. By the power rule, the derivative of 3x cubed minus x squared plus 1 is 9x squared minus 2x. Then we subtract the right expression, which is the numerator, 3x cubed minus x squared plus 1, times the derivative of the denominator. The derivative of cosine x is negative sine x. That's pretty much it. These negative signs undo each other, and with some trig substitution, you can get rid of the cosine squared x in the denominator. And that's the quotient rule. Speaking of trig, now that we know the quotient rule, we can find the derivative of the other 4 trig functions because they can all be expressed as fractions involving sine and cosine. I'm using the color coding from my trigonometry series just for this chart. For the derivative of tangent theta, the quotient rule is the denominator times the derivative of the numerator, minus the numerator times the derivative of the denominator, all divided by the denominator squared. This simplifies to cosine squared theta plus sine squared theta, which is 1, over cosine squared theta, which is secant squared theta, since secant is 1 over cosine. I'll show the derivation of the other trig functions using the quotient rule, but won't step through the details. You might need to know these. Check with your instructor. If you know the quotient rule and the circled trig identities, you can figure these out as you need them. Practice builds confidence. Here are the derivatives of the 6 trig functions. Let's check our agenda. We covered the 4-part trig cycle for the derivatives of sine and cosine. We covered the chain rule to find the derivative of composite functions, the rule you're likely to use more than any other. Then we went over the quotient rule and actually derived it from the product rule and the chain rule. We used the quotient rule to show the derivatives of the remaining trig functions, since they're all ratios that include sine and cosine. The last rules of differentiation are for exponentials and logarithms. Please note that all these atomic function types can be combined and used in all of these rules that allow us to combine functions in various ways. So, the next rules are for exponentials and logarithms. These rules are some of the simplest. Well, they've all been pretty simple, right? But there's a lot of background to review for it all to make sense. Exponentials and logarithms are usually covered in Algebra 2 or pre-calculus, but I'll do a thorough review of the topics needed to understand the rules of differentiation. Exponential functions have their independent variable x up in the exponent. The number on bottom is called the base. I'm color-coding the base green as a reminder that it's not a variable like x. It's a constant, such as 2. Don't confuse the exponential function, 2 raised to the power of x, with the polynomial or power function, x raised to the power of 2. They're different functions with different graphs and different derivatives. You can remember that exponential functions have their variable in the exponent. And in short, b to the x means multiply constant base b by itself x times. Let's assume we have b raised to the 7th power, as shown. The associative property of multiplication says that we can group the b's together like this and get the same result. So, b to the 7th equals b to the 3rd times b to the 4th. In general, when their bases are the same, we can multiply exponentials by adding their exponents. Let's graph some exponentials. When the base b is greater than 1, the exponential function value gets bigger and bigger as x increases. The slope is always positive. Functions like these are used to model exponential growth. When the base b is 1, the exponential function value y is always 1, because 1 to any exponent is 1, because 1 times itself any number of times is always going to be 1. And when the base is between 0 and 1, the function value gets smaller and smaller as x increases. Functions like this are used to model exponential decay. An exponential function with base b will always be symmetrical across the y-axis to an exponential function whose base is the reciprocal of b, like this example of 2 and 1/2. All the graphs of y equals some base b to the x pass through the very busy point 0, 1, because any base b raised to the 0th power will always equal 1. Here's an animation showing various exponential curves as the green base b changes. When b is greater than 1, the curve is always increasing. The higher the base b, the faster the increase. And as I mentioned, every curve passes through the circled point 0, 1. When base b is 1, the curve flattens out, because 1 raised to any power x will always be 1. And when b is between 0 and 1, the curve is always decreasing. Lower base values b decrease faster. So we have an exponential function y equals b to the x, where b is a constant and x is the independent variable. So given b, x, and a calculator, we can find y. But what if we know y and b and want to find x? For any function, when we find x given y instead of y given x, that's called taking the inverse of the function. Suppose we knew y equals 5.89 and wanted to find x. How would we do it? The inverse of the exponential function is the logarithm. The logarithm answers the question, what's the exponent? We write and say the logarithm function like this. X equals log base 1.473 of 5.89. It means x is the exponent on 1.473 that results in 5.89. These equations aren't solved by hand. We use a calculator, and before calculators, slide rules. Let me show you this again, emphasizing the inverse relationship. To solve this equation for x, we need to isolate x to get x equals something. But x is in the exponent. How do we get x out of the exponent? How do we undo exponentiation? By taking the logarithm. We'll take the logarithm of both sides, making sure that the bases match. To undo an exponent of base 1.473, we need to take the logarithm, base 1.473. Let's look at the right side of the equation. Remember, the log function answers the question, what's the exponent? Let's transliterate the right-hand side. What's the exponent on 1.473 that results in 1.473 to the x? Well, the answer is x. This is rather like asking what's half of twice x. The half and the twice undo each other, leaving x. And the logarithm base 1.473 undoes exponentiation base 1.473. So we get x on the right-hand side, which is exactly why we took the logarithm, to isolate the exponent x. To keep things even and balanced, we need to take the logarithm of the left side too. And we get log base 1.473 of 5.89, which our calculator will tell us is 4.58. Since exponentials and logarithms are inverse functions of each other, their graphs are symmetrical across the line y equals x. The exponential of base b is a mirror reflection of the logarithm base b across the dotted diagonal line y equals x. All inverse function pairs share this characteristic, not just exponentials and logarithms. So naturally, since all exponential graphs pass through the point 0, 1, because any base raised to the 0 power is 1, all logarithmic graphs pass through the point 1, 0, because the exponent to any base that results in 1 is 0. The associative property of multiplication tells us that b to the 7x can be expressed as b to the 3x times b to the 4x. Let's see what happens when we take the logarithm base b of both sides. Log base b of 7x is simply 7x. Like before, the log base b and the exponent on b cancel out, leaving just the exponent. And log base b of these two terms are 3x and 4x respectively. So the three terms we get after taking log base b are the three exponents of b, 7x, 3x, and 4x. And to write the resulting equation, we need to combine these terms by adding, not multiplying. That shouldn't be surprising. Logarithms effectively bring exponents down, and we already observed this property about multiplying exponentials. Let's go to an extreme and write b to the 7x as b to the x multiplied by itself 7 times. Now, when we take the logarithm base b of both sides, we get 7 distinct log base b of b to the x terms. That means that log base b of b to the 7x is 7 logs base b of b to the x. Or in general, log base b of b to the nx is n logs base b of b to the x. We can take the coefficient of x in the exponent and move it to the coefficient of the logarithm. We're almost ready for the rules of differentiation, but first another important property of exponential functions. Any exponential function can be expressed as an equivalent exponential function with any other base. So here's the graph of y equals 2 to the x again. We can get the exact same graph from an exponential equation that has another base, such as 3. So y equals 2 to the x can be expressed as y equals 3 raised to the something. Let's find the something by setting the expressions equal to each other. 3 raised to the something equals 2 raised to the x. Let's take the logarithm of both sides to isolate the red something variable. We need to be careful which base to use for the logarithm. We want to isolate the red something, so we'll take the log base 3 of both sides, since 3 is the base whose exponent we want to isolate. The left side simplifies to our red variable. On the right side, we take the exponent out and give us x log base 3 of 2. And that's the answer. 2 to the x is the same function as 3 raised to the log base 3 of 2 times x. And the calculator will tell us that log base 3 of 2 is about 0.63093. Here's the pattern for switching bases. The old base raised to the x power equals the new base raised to the power of log base new base of old base times x. So these are the same functions, and the point is, it's not the base that determines the shape of the exponential function, but a combination of the base and whatever coefficient the independent variable has in the exponent. The same curve can be described by lots of exponential functions having whatever base you choose. However, there's a very special exponential base whose value is about 2.718. It's so special that it has its own symbol, lowercase e. I'll use green as a reminder that e is a constant, like 2 or 3, not a variable. It's kind of a surprise that the constant e pops up in some simple formulas. It's a constant of nature, like pi. And I'll show you in a moment why e is so useful in calculus and why it's called the natural base. Here's a graph of the exponential function y equals 2 to the x, and here's y equals 3 to the x. Since e is between 2 and 3, it shouldn't be too surprising that y equals e to the x is between them. It's a very special base number, but its curve looks just like any other exponential curve. If we have a function y equals e to the x, we can find y given x like any other function, and we can invert it to express x in terms of y using the logarithm. If y equals e to the x, then x equals log base e of y. Well, the logarithm base e is also special, and it has a special symbol and name, the natural logarithm, or natural log. And for its symbol, instead of writing log base e, we write ln. I know that seems backwards, but it's from the Latin. Ln means natural log. So, log base e of y is equivalent to this expression, which can be pronounced as natural logarithm of y, natural log of y, ln of y, or even ln y. So once more, ln is a mathematical shorthand for log base e. The natural log also pops up surprisingly in some simple formulas. We'll see this limit again in a moment. When printed, ln can look like 1n, so when handwritten, you'll often see ln written in script or cursive with a loopy L like this. Here are some examples I found online. It's not a big deal, I just don't want you to be confused when you see the style, and I suggest you use it. Just write ln in cursive like it was a word. Now we're ready for the differentiation rules for exponentials. As usual, we'll find the slope at a red point by finding the slope between the red point and a nearby green point whose x-coordinate is x plus h. Then we'll take the limit as h approaches 0 and see what we get. Our function is 2 to the x, so we plug that into our limit equation. Note that we have 2 raised to the x plus h power. We can rewrite this as 2 to the x times 2 to the h, remember? Now we have 2 to the x twice in the numerator, which we can factor out to get 2 to the x times 2 to the h minus 1 all over h. Remember, we're taking the limit as h approaches 0, and 2 to the x won't change as h changes because there's no h in it, so we can pull it out of the limit. Now, I told you earlier that this limit is the natural log of this number, like this. And so, the derivative of 2 to the x is 2 to the x times the natural logarithm of 2. And in general, the derivative of b to the x is the natural log of b times b to the x. And that's a differentiation rule for exponents. We'll make it stronger in a moment, but it's good to know that the derivative of b to the x is the natural log of b times the original exponential function, b to the x. Quick, what's the derivative of 7 to the x? It's the natural logarithm of the base 7 times the original exponential function, 7 to the x. Easy. Now, what if the base were the natural base e? Same thing. The derivative of e to the x is the natural log of e times the original exponential function, e to the x. Well, what's the natural log of e? ln e means the exponent on base e, remember the base of the natural logarithm, ln, is always e, that results in e. So ln e is 1, because e raised to the power of 1 is e. This is not a special rule for e. Any log base b of b, that is, the logarithm of any number to its own base, is 1, because b raised to the power of 1 is b. So log base e of e is 1. We just have a special symbol for log base e, ln. So ln e equals 1. We substitute the natural log of e, which is 1, into our derivative and simplify to get the derivative of e to the x is e to the x, the only function that's its own derivative. Pretty neat. And that's why e is such a special exponential base. Now, on the screen are two equations or rules for derivatives of exponentials. The bottom is just a special case of the top for base e, since ln e is 1. But there's one more variation to consider, and then we'll have a single robust rule that will help us find the derivative of all exponential functions. Often, the exponent will not simply be x, but some function of x. This is very common in real-world applications of exponentials. We can't use the highlighted rule above. It applies only when the exponent matches the independent variable. For b raised to a function of x, they don't match, so the first rule won't work. We need to use the chain rule because we have a function f of x embedded within an exponential. Since we just covered the chain rule, I hope you'll excuse me if I jump straight to the conclusion here and say that we account for the daisy-chained functions by multiplying by the derivative of the exponent. So the derivative with respect to x of b raised to some function of x has three factors: the derivative of the exponent times the natural logarithm of the base b times the original exponential function. And this is the differentiation rule for exponentials to know, because it will work for any base, e or otherwise, and for any exponent, x or some function of x. Let me build a chart to show this is true. We'll put the general exponential function in this cell. It corresponds to any base, meaning not necessarily the natural base e, and a function of x in the exponent, as opposed to an exponent of simply x. As you'll see, the other three cells are simpler cases of this one. In the cell above, the base isn't necessarily e, and there's no function in the exponent, meaning the exponent is simply x. This cell represents the special case where the base is e and the exponent is a function of x. And finally, this cell represents the special case where the base is e and the exponent is simply x. We're going to find the derivative of each of these exponentials using the differentiation rule for exponents, the three-factor derivative from a moment ago. I'll step through the rule for each cell, and you'll see why we only need one rule. We'll start here with the most general form. The derivative of the exponential is always the derivative of the exponent times the natural log of the base times the original exponential function. And that's the three-factor solution that will always work. Let's apply the same rule to y equals b to the x. It's essentially the same function, except the exponent is x instead of f of x. No problem, we just write the three factors one at a time. We start with the derivative of the exponent. Well, the derivative of x is 1, so we can ignore the first factor. The second factor is the natural log of the base b. And the last factor is simply the original exponential function, b to the x. So the derivative of b to the x is ln b times b to the x. We used the same three-part rule, but the first factor went to 1, since the derivative of the exponent x is 1. Now let's find the derivative of e raised to the f of x. The derivative of the exponent times the natural log of the base. Since the base is e, ln e is 1, so the second factor is ignored. And the third factor is, again, the original exponential function. So the derivative of e to the f of x is f prime of x times e to the f of x. We used the same three-part rule, but the second factor went to 1, since ln e is 1. Now let's find the derivative of e to the x using the same three-part factor. The derivative of the exponent is x, and the derivative of x is 1, so the first factor goes to 1. The second factor is the natural log of the base. The base is e, and ln e is 1, so the second factor also goes to 1. The third factor is the original exponential function e to the x. So the derivative of e to the x is e to the x, the only function that's its own derivative. We use the same three-part rule, but the first factor went to 1 since the derivative of the exponent x is 1, and the second factor also went to 1 since ln e is 1. And that just left the third factor, which is the original exponential function. The point of this chart is that exponential functions come in several varieties, but you don't need to know several rules, just this one. It will give you the correct derivative for all exponentials, as long as you know that the derivative with respect to x is 1 and that ln e is 1. One rule to ring them all. Next is logarithms. The rules for logarithms can also be derived with the chain rule, but again, for the sake of expediency, please excuse me if I jump to the rules. Like we did for exponentials, we'll use the most general form of the logarithm function, having any base b, not necessarily e, and the argument can be some function of x, not necessarily plain x. The general differentiation rule for logarithms also has three factors that kind of correlate to the factors for exponentials. The first factor is the derivative of the function. That's the same. The second factor is 1 over the natural log of the base. This is the reciprocal of the factor for exponentials. And the third factor is 1 over the argument function f of x. The third factor isn't really that similar to the third factor in the exponential rule, but with practice you'll get it. The fractions are often combined, so you might see the rule like this. I'll keep it as three separate factors in the logarithm chart so you can see each factor clearly. We'll start with the general cell again in the lower left-hand corner and apply the new three-factor rule for logarithms. The derivative of the logarithm's argument, f prime of x, times 1 over the natural log of the base, times 1 over the argument. Like before, we'll use this rule as our pattern. It'll work for all the logarithm expressions. Let's apply it to y equals log base b of x. Here, the logarithm's argument is x, not a function of x. The first factor is the derivative of the argument. The derivative of x is 1, so we can ignore this factor. The second factor is 1 over the natural log of the base, 1 over ln b. And the third factor is the reciprocal of the argument, 1 over x. So the derivative with respect to x of log base b of x is 1 over natural log of b times x. Let's apply the rule to this cell and find the derivative of the natural log of some function of x. The first factor is the derivative of the argument, f prime of x. The second factor is 1 over the natural log of the base. The base of ln, the natural log, is e, and 1 over ln e is 1, so the second factor goes to 1. And the third factor is 1 over the argument. So the derivative of the natural log of some function of x is the derivative of the function divided by the function. Now let's apply the rule to the derivative of ln x. The first factor is the derivative of the argument, x, so it's 1 and can be ignored. The second factor is 1 over the natural log of the base. The natural log of base e is 1, so the second factor can also be ignored. This leaves the third factor 1 over the argument, so the derivative of ln x is 1 over x. So once again, a single rule for the most general logarithm will work for any of these special cases. And these are the differentiation rules for exponentials and logarithms that you should know. And so, finally, we've covered all these rules of differentiation. It's a lot of material. It's pretty much the entire first semester of calculus. Remember, calculus is all about performing two operations on functions, and we've just covered the first operation, differentiation. When we differentiate a function, the result is the function's derivative. The other operation is called integration. When we integrate a function, the result is the function's integral. As a preface to start learning about integration, I need to introduce the antiderivative. Suppose we're given a function and told that it's a derivative, f prime of x. What, then, is f of x? In other words, what's the function whose derivative is f prime of x? If f prime of x is the derivative of f of x, then f of x is the antiderivative of f prime of x. The second calculus operation, integration, depends on being able to find antiderivatives. In fact, the integral is the antiderivative. This is the important topic for the second half of calculus, because differentiation and integration are almost exact opposites of each other. But let's start simply. Suppose f prime of x equals x squared. How can we find out what f of x is? Just to be clear, we're not trying to find the derivative of x squared. The power rule tells us the derivative of x squared is 2x. Easy. Instead, we need to use the power rule backwards. We're looking for the function whose derivative is x squared, or the antiderivative of x squared. As a reminder, here's the power rule shortcut for when x to the n has a coefficient k. The derivative with respect to x of k times x to the n is kn times x to the n minus 1. Remember, we bring the exponent downstairs, multiply by any coefficient that's already there, and then reduce the exponent by 1. So imagine that we did this to some function, f of x, and the result was f prime of x equals x squared. What function, f of x, did we start with? Let's muscle through the power rule backwards. To take the derivative of a power, we reduce the exponent by 1. So to take the antiderivative of a power, we'll need to increase it by 1. So we have something x cubed. Let's use our imaginations for a moment and see what happens when the green question mark is 1. That would make f of x equal to x cubed, and f prime of x, the derivative of x cubed, equal to 3x squared. 3x squared is 3 times larger than f prime of x we're targeting. So we need a factor that will reduce it by 1/3. So the green coefficient must be 1/3. It's always easy to check antiderivatives. Just take its derivative and see if you get the function you started with. In this case, the derivative of 1/3 x cubed does indeed equal x squared. So the antiderivative of x squared is 1/3 x cubed. In general, the antiderivative of kx to the n is x to the n plus 1 times the coefficient k divided by n plus 1. You may see this written as kx to the n plus 1, all over n plus 1. Same thing. Now, there's just one glaring challenge staring right at us. This formula won't work when the denominator of the fraction is 0. Let me build a chart that shows the antiderivatives of simple powers of x to highlight the pattern and challenge. Let's start with the derivative of x cubed. To find the antiderivative, we add 1 to the exponent and then divide by that new number, 1/4 x to the 4th. In a few moments, we're going to make a small adjustment to this expression and the others on this chart. So the antiderivative of x cubed isn't exactly 1/4 x to the 4th, but you still need to know this antiderivative formula for powers. If the derivative is x squared, then the antiderivative must be 1/3 x cubed, plus the adjustment. We'll cover it soon. I won't mention it again until then. This antiderivative, 1/3 x cubed, was the example we muscled through to get our antiderivative formula. Next is the derivative of x to the first power, which is just x. Following the formula, the antiderivative of x must be 1/2 x squared. So far, so good. Here the derivative is x to the 0, which is 1. The antiderivative of 1 is x, since the derivative of x is 1. Of course, using the formula yields x, since 1/1 times x to the 1 is simply x. Now, when the derivative is x to the -1, then this is the same as 1/x. And here's where the formula breaks down, because it results in a denominator of 0. So this is an undefined expression. We'll come back to it, but let me add a few more to the chart to show that the antiderivative formula for powers works for every other power, positive or negative. It also works for fractional powers, but I don't show any on the chart. It works for everything except when the exponent is -1, which corresponds to 1/x. We cannot use this formula to find the antiderivative of 1/x. But 1/x does have an antiderivative. What is it? You might remember this chart, where we covered the differentiation rules for logarithms. Here we showed that the derivative of the natural log of x was 1/x. That must mean that the antiderivative of 1/x is the natural log of x. Almost. This one needs another slight adjustment in addition to this slight adjustment. But we'll cover the special natural logarithm adjustment right now. Here's the graph of f prime of x as x to the -1, or 1/x. I graphed it in pink because it's the slope. The slope of what? Its antiderivative, which is the natural log of x, shown in the white curve. Here's where the challenge arises. The natural log function is defined only for positive x values, the right half of the graph. But 1/x is defined for positive and negative values, but not 0. So we need a white function curve on the left side of the graph that answers the antiderivative question. What function has this derivative? Let's note that the pink curve 1/x is symmetrical across the origin, and so can be spun around 180 degrees without changing. This means that every pink point has a twin across the origin with opposite coordinates, and so the white function will have reflected points across the y-axis with the same slope. Thus, our white function, the antiderivative of 1/x, is the natural log of the absolute value of x. This function is the antiderivative that works perfectly for both positive and negative x values. So here's the general antiderivative rule for powers. The top rule, the bump up the exponent rule, works all the time except when n, the exponent on x, is -1. When n is -1, then that's the antiderivative of k/x, which is k times the natural log of the absolute value of x. We still have this adjustment I promised, so let me explain what it is and why it's needed. I'll illustrate by taking the antiderivative of a polynomial. We're starting with polynomials because they're easy and straightforward. We'll cover the antiderivative of other function types later. The addition rule for differentiation says that the derivative of the sum is equal to the sum of the derivatives, and the same rule applies to antiderivatives. The antiderivative of the sum is equal to the sum of the antiderivatives. So we can find the antiderivative of this function term by term. We'll go through these quickly. The antiderivative of 8x cubed is something x to the 4th. Coefficient 8 divided by 4 is 2, so 2x to the 4th. It's always easy to check by going backwards. The derivative of 2x to the 4th is equal to 8x cubed, so we can be confident that the first term is right. Next term, the antiderivative of 3x squared is something x cubed. Coefficient 3 over the new exponent 3 is 1, so the second term is plus x cubed. The term minus 6x has antiderivative something x squared. Negative 6 divided by the new exponent 2 is negative 3, so the third term of the antiderivative is minus 3x squared. And the last term is 1, which we can think of as 1x to the 0, so the exponent of the antiderivative is 1, and the coefficient is 1/1, or 1, so just plain x. And this checks out. The derivative with respect to x of x is 1. Well, it looks like we're done. We know that f prime of x is the derivative of f of x, and that f of x is the antiderivative of f prime of x. Here's the antiderivative we found, and we can validate by taking the derivative term by term. Perfect, we nailed it. But now let's consider the same function, f of x, except it has plus 1. All the derivative terms are the same. And we add the derivative of 1, but the derivative of 1 is 0 by the constant rule. So the derivative of this new f of x is the same as the previous one. And it's the same if we add 2 or subtract 1, or add or subtract any constant. All of these functions have the same derivative, the derivative we started with, 8x cubed plus 3x squared minus 6x plus 1. Here's what's going on. Here's a graph of the antiderivative we found, 2x to the fourth plus x cubed minus 3x squared plus x. And here's the graph of the derivative we started with, 8x cubed plus 3x squared minus 6x plus 1. Remember, we started with this pink derivative and we backed into the white equation by taking the antiderivative. The pink derivative curve looks reasonable. It says the derivative is 0 at these 3 points where the white slope is 0. Now let's look at the next equation up, the one that ends with plus 1. Note that this simply translates the white curve straight up by 1 unit. The slopes don't change. Everything is just shifted up. This makes sense. Both equations yield the same pink derivative. Same with the plus 2 version and the minus 1. We can add any positive or negative constant to a function without changing its derivative, because adding a constant just moves the entire curve up or down without changing its slope anywhere. Thus, each member of this family of functions has the same derivative. So when we find the antiderivative of the right function, which one do we choose? Well, we designate the whole family by adding plus c, where capital C represents any constant and is called the constant of integration. This is true for all antiderivatives, not just the antiderivative of powers and polynomials. Every function has exactly one derivative, but every function has an infinite number of antiderivatives, because they can be shifted up or down by constant c and still have the same derivative. So we specify the whole family of functions by including the plus c constant of integration when we find antiderivatives. So the adjustment I promised is the constant of integration, plus c. It should always be included in antiderivative functions. And so our general antiderivative rule for powers needs to be updated to include the constant of integration. Regarding antiderivative notation, when we're given a function called f prime of x, it seems pretty clear that its antiderivative would simply be the function name f without the prime indicator. Since taking the derivative adds a prime symbol, taking the antiderivative, reasonably, it seems, removes a prime symbol. But when a function doesn't have a prime symbol, how do we denote its antiderivative? Well, the convention is that we capitalize the function letter. So capital F of x is the antiderivative of lowercase f of x, and the derivative of capital F of x is lowercase f of x. When we intend to denote the derivative of a function, f of x, we're already familiar with expressing this as f prime of x and as d by dx of f of x. For the antiderivative of f of x, we can express this as uppercase f of x, as already mentioned, or we can use this new calculus notation. This is the integral symbol. It's not a Greek letter, it's an elongated S for sum. We'll get into the details in a few minutes. The function whose antiderivative we're finding is called the integrand. When I introduced the antiderivative concept, I called this function f prime of x to emphasize that it's already the derivative and that we are going backwards from it. When you see an integral expression, the integrand won't have a prime symbol as a reminder. The integral symbol means find the antiderivative of the integrand, and the differential dx denotes the variable of integration. This expression has an intuitive interpretation that we'll be ready for in just a moment. Here's our sample function, and we were asked what function has this derivative. We applied the power rule for antiderivatives term by term and got this function, the antiderivative. We expressed the antiderivative operation with the integral symbol like this. The integral of a function yields its antiderivative. Remember to include the constant of integration. So the second calculus operation, integration, is finding the antiderivative. But it's so much more than that and has interesting applications that make it suitable for solving lots of real-world problems. I want to show you another, more insightful interpretation of integration, but I need to start in kind of a strange way. I'll draw a coordinate system where the horizontal axis denotes time in seconds, and the vertical axis denotes velocity in meters per second. Suppose we have a particle. Physicists and engineers use particles in thought experiments like this so they don't have to worry about measuring from the front edge or back edge. It's just a dimensionless speck, so they're all the same. So this particle is moving at a constant velocity of 2 meters per second for 8 seconds. What's the particle's displacement after these 8 seconds? Displacement is the vector form of distance. So for this example, you can think of displacement as distance, since the particle is moving in one direction along a straight line. This is a pretty easy problem. 2 meters per second times 8 seconds, the unit seconds cancels, leaving 16 meters. As it turns out, the area under a velocity curve is always equal to the displacement, 2 high times 8 wide, 16. Now, to illustrate the points I'm making, I'm using displacement and velocity. But there are many phenomena that fit this model. For example, I could have used total electrical charge and electric current, or population and growth rate, or energy and power. But I chose displacement and velocity because people have an intuitive understanding. So please don't think we're just learning how to solve distance problems. The calculus tools we're learning can be applied to many types of situations. So this red area representing displacement is intuitively simple when the velocity doesn't change, like in this example. But what if the particle started at 2 meters per second and accelerated smoothly to 4 meters per second? Not as straightforward unless you realize all you have to do is find the area. Then it's still simple because the velocity line is straight, and you can use simple geometry to find the displacement for this graph is 24 meters. This area is still 16, and this triangle is 8. That's geometry, not calculus. Okay, what if the velocity over time is described by a curvy line? Now we've got a challenge. We know the function f of t. It tells us the particle's velocity at any point in time. And there must be some other function, I'll call it capital A of t, that tells us the red area up to any point in time, t. The A stands for area. But we don't know what function A is. Well, we still want to know the area, so here's one way to attack the problem. We'll start by estimating the red area under f of t by dividing it into vertical rectangles. It's easy to find the area of a rectangle. Then we'll add up all the rectangular areas, and that will be our estimate of the red area. For the sake of convenience, let's make the width of each rectangle 1 second. So delta t equals 1, and we'll draw 8 rectangles since the motion lasted 8 seconds. For clarity and consistency, we'll make the height of each rectangle be the function's value at the rectangle's left edge. Here's what I mean. For the first rectangle, its height is this distance, which is f of 0, because its left edge is at time t equals 0. The width is delta t, so the rectangle's area is f of 0 times delta t, height times width. The second rectangle will have height f of 1, its left edge. Its area is f of 1 times delta t, and so on for the other 6 rectangles. Each rectangle is an estimate of the red area over its width, delta t. The height of each rectangle is the function's value, f of t. So the total area of the 8 rectangles, which is our estimated area for red, is the sum as t goes from 0 to 7 of f of t delta t. Add up all 8 of the height times widths. We end with 7 and not 8 because we started counting at 0. 8 rectangles, 0 through 7. Well, that might be a pretty good estimate, but each rectangle fits the curve imperfectly, so there's going to be some error in our estimate. More narrower rectangles will more closely fit the curve and provide a better estimate. So we'll let delta t get smaller and smaller. Maybe this made you think of the method we used to estimate the slope of a curve at a point. We let the distance between 2 points get smaller and smaller, all the way down to the differential dx, and that's what we'll do with these rectangles. We'll make the error in our estimate approach 0 by using a larger and larger number of rectangles having narrower and narrower widths, until we get to the limit as the width approaches 0, the differential. In this example, our independent variable happens to be t instead of x, so the differential will be dt. Adding up an infinite number of things isn't easy. It could take all day. When we had 8 rectangles corresponding to times t equals 0 through 7, we used this summation. But calculus has some special notation to add up a continuum of differentially small numbers. It's the integral symbol from the antiderivative. As you'll see, we treat it a lot like the summation symbol. For example, the summation expression above includes the lower and upper bounds of the summation here, and the integral symbol gets lower and upper bounds also. For our example, we're starting at time t equals 0 and going all the way through to t equals 8. This represents adding up all the infinitely many differential rectangles between 0 and 8. In the summation expression, we're adding up all the rectangular areas, which are height times width, f of t times delta t. And we do the same thing in the integral expression, except the width is dt instead of delta t. We only apply the integral operation to differential widths, and this integral is equal to the function a of t. The equation says the area under the curve of f of t up to t equals 8 is the integral of f of t dt from 0 to 8. I'm telling you this is true, but I want to convince you. I think this will give you a better understanding of this extremely important calculus concept. Let's consider our velocity curve again. We know the function f of t describes the particle's velocity at any time t. Here's our function a of t that represents the area under the curve up to t. It looks like t is 3, but it doesn't matter. It's got to be something. Now, suppose I draw our very thin rectangle here. Its width is dt, the differential change in time t. I'm drawing the rectangle kind of thick so we can see it, but its width dt is approaching 0, so invisibly thin. Its height is f of t, the velocity of the particle at time t, and the thin rectangle's area is dA, the differential change in area due to the differential change in time dt. Now, if your attention is drifting, please perk up. This could be the most important minute in the entire video. We can write an equation relating these three variables. dA equals f of t dt, or area of rectangle equals height times width. Now, let's divide both sides by dt to get dA by dt equals f of t. So we have an unknown function, a of t. We'd like to know what it is, but we don't. However, we know its derivative is f of t. So if f of t is the derivative of a of t, then a of t must be the antiderivative, or integral, of f of t. We find the cumulative area under a function curve using the antiderivative of the function. And that's the second, I think, more insightful interpretation of integration, finding the area under a function's curve. Let's try this out with our earlier examples. Now, I'm going to be a little sloppy because I'm anxious to show you how well this works, but I'll clean up the sloppiness afterwards. Here's the constant velocity example. F of t equals 2, since the velocity is a constant 2 meters per second. The area function, a of t, we just discovered, is the antiderivative of f of t. So a prime of t equals f of t, and we want a of t. So let's take the antiderivative of both sides, and we get a of t equals 2t. The antiderivative of 2, remember, is 2 times the independent variable t, so 2t. As always, it's easy to check by going backwards using the power rule that the derivative with respect to t of 2t gets us back to 2. And the derivative of a of t is a prime of t, so we're all balanced. So we have a function for a of t. Let's plug in 8, and we get 16 meters, which is the same answer we got earlier through algebra. Now let's try the velocity line with the non-zero slope. By inspection, we can see that the function for the line is f of t equals 1/4 t plus 2. This is from algebra, y equals mt plus b. The slope is rise over run, or 1/4, and the y-intercept is 2. This is algebra, not calculus, so I'm not covering the details. F of t is equal to a prime of t, but we want a of t. So let's take the antiderivative of both sides to get a of t equals 1/8 t squared plus 2t using our power rule for antiderivatives. Plug in 8 and we get 1/8 of 64, which is 8 plus 16, so 24 meters like before. Okay, we should be convinced that given a function f of t, its antiderivative will yield the function denoting the area under its curve. Now, in my enthusiasm to show you the relationship between a function's antiderivative and the area under the function's curve, you may have noticed that I sloppily skipped over two important details we'd mentioned earlier. First, the constant c we add to the antiderivative to show that there are a multitude of functions all having the same derivative. Second, the lower and upper limit we added to the integral symbol to denote the range over which we were summing up the antiderivative's differential rectangles. Let me address these considerations by modifying our problem slightly. Suppose now we're interested in the area under f of t between t equals 2 and t equals 8. This would represent just the particle's displacement that occurs between 2 and 8 seconds. How can we find this new, smaller red area? Well, it's this larger red area that we've already found, a of 8, minus this smaller red area, a of 2. The difference is the area we wanted to find. 8 is the upper bound and 2 is the lower bound. The notation means we're going to start with the differential rectangle at t equals 2 and sum up all the rectangular areas up to t equals 8. And we accomplish this by taking the antiderivative of the function f of t. We already did this. We relabeled f of t as a prime of t to emphasize that its antiderivative was a of t, the function that returns the cumulative area under f of t. And the antiderivative of f of t is 1/8 t squared plus 2t plus c. We evaluate this antiderivative at t equals 8 and subtract the value we get at t equals 2. Here's how we write the expression. This vertical bar is called the evaluation bar, and when solving an integral, it means to plug the upper limit into the expression to the left of the bar, then subtract the expression's value at the lower limit. The expression to the left of the evaluation bar must be the antiderivative of the integrand, the function whose area we're evaluating. So let's find the area between t equals 2 and 8 by solving this integral. First, we plug in t equals 8, then we subtract for t equals 2. The top expression is 8 plus 16 plus c, so 24 plus c. The bottom expression is 1/2 plus 4 plus c, so 4.5 plus c. When we subtract, we get 19.5. Please notice the constant of integration, c, cancels since we subtract one from the other. And so the answer to our question, what's the red area between t equals 2 and 8, is 19.5, which represents 19.5 meters in the context of our velocity problem. Now, let's put everything together and add some precision to our calculus vocabulary. When an integral expression has no upper or lower bounds, that's called an indefinite integral. That's easy to remember because we're indefinite about what the boundaries might be. An indefinite integral is equal to the antiderivative of the specified function and includes plus c, the constant of integration. An indefinite integral is like the answer to a quiz question. What function has f of x as its derivative? Since every function has infinitely many antiderivatives, we specify the entire family of functions by including the plus c constant of integration when solving indefinite integrals. When an integral expression has boundaries, it's called a definite integral. A definite integral is equal to the antiderivative of the specified function at the upper limit minus the antiderivative of the function at the lower limit. We can write this difference these two ways. They mean the same thing. So when we solve a definite integral of a function f of x, the first step is to find the indefinite integral, that is, the antiderivative of f of x. because we have to evaluate it at the upper and lower boundary to solve the definite integral. And as we've already seen, the constants of integration plus c always cancel when we subtract. So it's okay if you leave them off of your definite integral expression like this. And so, while the indefinite integral is a function with plus c, a definite integral is a number, the number that represents the area under the curve f of x between the lower and upper boundary. And of course, to find the number, you need the function. Here's a summary chart. The indefinite integral is a function having the integrand as its derivative. It includes the constant of integration. The definite integral has bounds and is a number, the antiderivative evaluated at the upper bound minus the antiderivative at the lower bound. So to calculate the definite integral of a function, you first need to know the indefinite integral of the function, which is the function's antiderivative. Let's do another problem. Here's a function f of x equals 0.1 x squared minus 1.5x plus 4. We're just using polynomials for now because they're so easy. We'll get to other types of functions later. Suppose we need to know the area beneath the curve between x equals 2 and x equals 9. When we examine the area, a question immediately presents itself. What happens when the function has a negative value? I've been saying area beneath, but that's not literally the case. As we'll see, the integration operation will treat areas corresponding to negative function values as negative areas between the function curve and the x-axis, like this. So the green area is positive and the red area is negative. So to be precise, we can say that the definite integral yields the signed area, such that areas above the x-axis are considered positive and areas below the x-axis are considered negative. Okay, let's find the signed area. We need to start with the indefinite integral of f of x. Its antiderivative we call capital F of x. We use the same rule as before. For each term, bump up the exponent and divide any coefficient by the new bumped up exponent. We write the definite integral with its boundaries 2 and 9 and write the antiderivative with the evaluation bar having the same boundaries. Please don't put f of x in here and evaluate it at the boundaries. You've got to use the antiderivative of f of x to find the area under f of x. That's why the first step of any integration problem is to find the antiderivative, capital F of x, of the integrand, lowercase f of x. And that's the function we evaluate to find the area without the plus c. I apologize if I'm over-explaining. I don't want anyone to struggle with the parts of calculus that I struggled with. If I repeat something, it's probably because I wish it had been repeated more than once to me. Anyway, we're ready to find the area. We evaluate the antiderivative at the upper boundary, 9. It's just algebra, so I won't show details. Negative 0.45. Next, we evaluate the antiderivative at the lower boundary, 2. It's 5.27. Then subtract upper minus lower. Negative 0.45 minus 5.27 equals negative 5.72. And that's the signed area of f of x between 2 and 9 that we needed to find. This application of definite integrals that we've already seen several times is so important that it has a special name, the Fundamental Theorem of Calculus. In plain English, it says that the definite integral of f of x from a to b is equal to the difference between the antiderivative of f of x evaluated at b and the antiderivative of f of x evaluated at a. It's interesting and insightful to see why this works. Here's our original function. I'm making the lowercase f pink to easily identify it as a pink derivative curve. Here's the antiderivative we found, capital F of x, and here's the graph of the antiderivative, white. Well, as I keep saying, there are many functions having the pink derivative. The one I plotted is the one where the constant of integration c is 0. So the pink curve is the derivative of the white curve. That looks reasonable. The white curve is flat here with 0 slope, and the pink derivative is 0. In the first half of this video, when we found the derivative, we started with white and found pink. Now in the second half, when we find the integral, we're starting with pink and finding white. And calculus tells us that the value of the white curve at a point represents the area under the pink curve up to that point, at least when the white curve crosses the origin, so the area starts with 0 at x equals 0. Okay, let's try it out by visual inspection. Let's look at x equals 1. Capital F of 1 is about 3.28. Just plug 1 into capital F of x to get 3.28. Let's eyeball the area under the pink curve up to x equals 1. There's 1, 2, we're missing a little bit of 3, but we have this extra up here. I hope it seems reasonable that the area of green is 3.28. Now let's look at x equals 2. Capital F of 2 is about 5.27. We found this a few moments ago by plugging 2 into capital F of x. This one's a little trickier to estimate, but you can pause if you'd like to convince yourself that 5.28 is a reasonable value for the green area between x equals 0 and 2. When we go up to x equals 3, capital F of 3 equals 6.15. Between 2 and 3, this white value went up by a small amount, 0.88. And that corresponds to this new area under the curve between x equals 2 and 3, 0.88. Where the slope of capital F of x is negative, the value of pink f of x is negative. Of course, because the pink function is the derivative of the white function. For example, between x equals 7 and 8, capital F of x decreases. 1.06 minus 2.68 is negative 1.62, which corresponds to the negative area between 7 and 8. This is how we were able to integrate pink f of x between 2 and 9 by simply evaluating the antiderivative's value at x equals 2 and 9 and subtracting. The difference in the antiderivatives is the definite integral of the function. I confess I was confused and amazed in high school when I learned this. How can evaluating a white function at only 2 points tell me everything that's gone on with another pink function between those 2 points? The explanation that I wish I'd understood back then is that a key property of the antiderivative function is that it's like a running total of its derivative. Here's an example. Suppose you ran your own business for a very long time, and you have a business bank account whose balance increases or decreases daily. Here I'm illustrating a multitude of green and red rows, each representing the daily change to the account balance, green for positive, red for negative. Let's imagine you need to determine how the balance has changed between two far-apart dates, A and B. You have to add up all the hundreds of daily changes that occurred between those two dates. But you've also kept a running total of your bank balance at the end of each day. So with this, you just need to find the two balances on the boundary days and subtract to determine the cumulative change that occurred between the two dates. That's how definite integrals work and why the Fundamental Theorem of Calculus is true. Since the antiderivative is a literal running total of its derivative, you just need to find the antiderivative's value at the two boundary points, and their difference will be the cumulative sum or area of the original function. And that brings us to the third interpretation of integration, adding up a lot of tiny amounts using the running total characteristic of the antiderivative. This is a lot like interpretation number 2, finding the area under a curve, since it's adding up a lot of tiny rectangular areas. But adding up a lot of tiny things is a bit more general, and I think if you keep this interpretation in the back of your mind, you'll be well served by recognizing when calculus can be used to solve a problem you're facing. I'd like to formalize our progress so far and plot out the remainder of our calculus journey. Here's a somewhat cramped summary of the rules of differentiation we covered in the first half. I'll just note that the first 5 represent distinct atomic function types. The last 3 represent the ways in which functions can be combined: adding, multiplying, and compositing. Many of these differentiation rules have corresponding integration rules. For example, we reversed the power rule for differentiation and figured out the rule to find the integral of a power function. So, given a power function, we can find its derivative or integral. This is why all of the examples so far have been polynomials, because the power function is so easy for both calculus operations. The trig functions are also easy. When graphing the sine and cosine functions, the derivative of a function is the curve to that function's left. So naturally, the antiderivative is the curve to the function's right. Just remember the constant of integration. There's also a constant rule for integration. It says that for a constant times a function, like k f of x, the integral is the constant times the integral of the function. We usually remember, pull the constant out of the integral. And the addition rule has an application for integrals. It says the integral of the sum is equal to the sum of the integrals. This is similar to the differentiation rule that says the derivative of the sum is the sum of the derivatives. For exponentials, it's easy to integrate a simple function, such as b to the x. The integral is b to the x over the natural log of b plus the constant of integration. I'd be remiss if I didn't point out that for the special case of the general rule, e to the x, the derivative is e to the x, and so the integral of e to the x is e to the x plus c. E to the x is its own derivative, and therefore its own integral. But from here, integration gets much less straightforward in contrast to differentiation. The truth is, finding derivatives is easy. If you're watching this video before taking calculus class, good for you, get prepared. You can be an expert on derivatives before your class even starts, because taking derivatives is so easy. It just takes practice, which you won't get from this video. I'm trying hard to show the fundamentals of calculus in a visual, interesting, memorable way. But you're not going to get the practice you need for proficiency just by watching me. I'll mention some practice resources at the end of this video and provide links in the description. So, finding derivatives is easy, but finding integrals isn't always easy. We'll do a few more easy integration problems, and then I'll show you some difficult integrals and describe some of the techniques used to solve them. There's a technique called integration by parts that roughly corresponds to trying to apply the product rule in reverse, and another technique called u-Substitution that tries to apply the chain rule in reverse. Because so many real-world engineering, science, and finance problems involve function products and composites, these rules are used a lot, and you should become familiar with them and comfortable using them. I'll cover these techniques after a few simpler problems. Let's solve a simple definite integral. The integrand consists of three terms, so we'll apply the addition rule to integrate each term separately. Each mini-integral has the same limits of integration as the original integral, -1 to 2. The middle integrand, 2x squared, has a constant, so we'll apply the constant rule and pull the coefficient out of the integral like this. Actually, the third integral also has a constant because we can consider the function 4 to be 4x to the 0. But an antiderivative shortcut you should be familiar with is to multiply a standalone constant like 4 by the variable of integration, x. So the antiderivative of 4 with respect to x is 4x. Let's go ahead and start with the third integral. We'll evaluate 4x from -1 to 2. The middle term becomes twice the integral of x squared, which is 1/3 x cubed, evaluated from -1 to 2. And the antiderivative of sine x is negative cosine x, evaluated from -1 to 2. The rest is just arithmetic, but please proceed carefully and deliberately. I didn't intend it when I made up this problem, but there are several opportunities to get confused with positive-negative signs. The second term is subtracted. The first antiderivative has a negative sign, one of the boundaries is negative, and of course when we evaluate the integral, we subtract the lower value from the upper. So let's go slowly, left to right. We'll plug in the upper boundary, 2, into a negative cosine x, and get approximately 0.4161. The cosine of 2 radians is actually negative 0.4161, but we've got the negative sign here, so the expression is positive. When we plug in the lower boundary, we get negative 0.5403. The cosine of -1 is approximately 0.5403, but again we have the negative sign, so negative 0.5403. And we need to be careful because when we subtract bottom from top, Subtracting a negative is the same as adding a positive, so the difference is positive 0.9564 to 4 decimal places. Let's go on to the second integral. Plug in 2 and we get negative 2 times 1/3 of 2 cubed. This turns out to be negative 2/3 of 8, which is approximately negative 5.333. I'm carrying 4 digits after the decimal. When we plug in negative 1, we get positive 0.6667, and when we subtract these terms, we get negative 6. Now for the last term, 4x evaluated from negative 1 to 2 is 8 minus negative 4, which is 12, to any number of decimals. Now we just add up the 3 subtotals, and since we've already been careful with the signs, we add across to get 6.9564, and that's the value of the definite integral. Let me point out some slightly different mechanics that result in the same answer. Instead of using the addition rule for integrals to break the problem into 3 distinct smaller integrals like we did, each having its own expression to evaluate at the upper and lower bounds of integration, we can simply add the addition rule for integrals to the terms one at a time into one expression, and evaluate the entire expression from the lower to the upper bounds, like this. When evaluating an expression with multiple terms, a shortcut you might see is to use square brackets around the expression, and place the bounds on the right square bracket and omit the evaluation bar. It means the same thing. When we evaluate at the bounds, we get the same numbers as before. We just do the arithmetic in a different order. It's the same answer, of course. We can use the same technique to specify indefinite integrals. Remember, this means no upper or lower bounds, so the answer is going to be a function, not a number, since we won't be plugging any boundary values into the antiderivative. Simply find the antiderivative of each term one at a time and remember the constant of integration, which is needed for every indefinite integral. To finish the topic of integration, we need to cover these last 2 integration techniques. We use them for integrands for which there is no straightforward rule to apply, usually when the integrand is a product of functions or is a composite function. These are usually more challenging integrals to solve and in the real world much more commonly encountered. Let's look at a different problem we did earlier, where we found the derivative of the square root of 5x squared plus 3 using the chain rule. We use the chain rule because we have a composite function, a function, 5x squared plus 3, within another function, square root. I'm rewriting the square root of 5x squared plus 3 as 5x squared plus 3 to the 1/2 power. And as a reminder, here's the chain rule. The inner function, g of x, is the polynomial. The outer function, f of x, is the square root. We started with the derivative of the square root, outer function, to get 1/2 5x squared plus 3 to the negative 1/2. This is the power rule for derivatives, and the result is df by dg. Then we need to multiply by the derivative of 5x squared plus 3, which is 10x. This is dg by dx. We can combine terms and then, if you like, exchange the negative 1/2 exponent for 1 over square root. And that was our derivative. Now, suppose we want to go backwards and find the integral. Well, nothing we've covered so far comes close to helping us solve this integral. We know what the answer should be, this function that we started with, plus c. As I've said, finding derivatives is always easy, but finding integrals can often be difficult. Let me show you an approach to solving difficult integrals called u-Substitution. U-Substitution is a good technique to consider if the integrand is a product of functions. We choose an expression within the integrand and replace it with a new expression called u. I'm not sure why the letter u was chosen, but that's what everybody uses, so we should get used to it. There are 2 expressions to choose from, 5x and 5x squared plus 3. I'll mention strategies for how to choose u in a moment, but for now I want to show you the mechanics of the technique, and we'll use u equals 5x squared plus 3. Now, our short-term goal is to rewrite the integrand in terms of u, without any references to variable x. After you write down your u equals statement, write the expression for du by taking the derivative of both sides with respect to x. Du equals 10x dx. Then rewrite that equation to isolate dx. dx equals du over 10x. Now, let's plug what we know back into the integral. We still have 5x. We haven't done anything with it yet. Next, we multiply by u to the negative 1/2, since u equals 5x squared plus 3. And in place of dx, we substitute its equivalent in terms of du over 10x. Well, our 5x and 10x can reduce to 1/2, which is a constant we can pull out of the integral. So we have 1/2 times the integral of u to the negative 1/2 du. Great, we don't have any more x's. Everything is in terms of u, so we can integrate with respect to u using the power rule for integrals. We bump up the exponent by 1 and divide by the new exponent. We have 1/2 times u to the 1/2 over 1/2. These 1/2s cancel, and that leaves us with u to the 1/2. Now, let's reverse the u-substitution and plug 5x squared plus 3 back in for u. We get the square root of 5x squared plus 3 plus c, which is indeed the function we started with, adding the plus c for the indefinite integral. So on the top line, we use the chain rule to find the derivative of the square root of 5x squared plus 3. Then on the second line, we used u-substitution to integrate the derivative, and, as expected, we got back to the function we started with, plus c. I'll walk through the steps for u-substitution, but first please notice this pattern. When we differentiate using the chain rule, we multiply by the derivative of the inner function. So the derivative of sine 2x is 2 cosine 2x. Remember, the derivative of sine something is cosine something, but the chain rule reminds us that we need to also multiply by the derivative of that something. Let's look over at the u-substitution problem. There's not always an inner and outer function, but rather an expression we choose for u. At this step, where we isolate dx, we'll always get du divided by the derivative of the u term with respect to x. Just to help you remember, differentiating with the chain rule and integrating using u-substitution are opposite operations. Since we multiply by a derivative with the chain rule, remember that we divide by a derivative with u-substitution. So we choose the expression for u, knowing that we're going to divide by its derivative, and by doing so, hopefully, make the function simpler. Let me walk through the steps for u-substitution, then we'll solve another problem. With practice, you can do some of these in your head, but writing them down is good for starting out and gaining confidence. First, choose a function in the integrand to replace with u. Choose a function whose derivative will help simplify the integrand when you divide by it. You'll get better and develop an instinct for what works with practice. Then differentiate the function you chose for u and isolate dx. Actually, this step will always yield du divided by the derivative of u with respect to x. This is why many calculus students just remember to divide by the derivative of u when using u-substitution. The next step is to rewrite the integral, plugging in u for its function and replacing dx with its expression in terms of du. The goal is to remove x entirely from the integrand, so the integrand is in terms of u. This should result in a simpler integration problem. If you cannot get rid of all the x's, then make a different choice for u. Please note that there's no guarantee u-substitution will work. Unlike differentiation, where there are always straightforward rules to follow, integration often requires some imagination and a flair for creative problem solving. Next, go ahead and integrate the new integrand with respect to u if possible. We started with an integral of a function of x with respect to x. After u-substitution, we have a function of u and want to integrate with respect to u. It should be a simpler integral. If you can't integrate, then make another choice for u, or perhaps the problem can't be solved with the u-substitution method. If you can integrate the result, do so, and replace u with its original x function, and that's the answer to the original integration problem, plus c. Let's do another problem. Let's find the integral of 4x e to the x squared. Interesting, the exponent has an exponent. Well, let's dig in. There are several choices for u that include x. 4x, e to the x squared, or just x squared. Remember that we're going to end up dividing by our choice's derivative. That's really what you should be thinking about when choosing u. When I divide by its derivative, will that help me get rid of x's? Choosing 4 or 4x won't help. E to the x squared. That's a composite function that we'll need the chain rule to differentiate. Not impossible, we'll come back to it if we need to. X squared looks promising. Its derivative is 2x, which will cancel nicely with the 4x. So we'll start by trying u equals x squared. Step 2 is to differentiate u. We get du equals 2x dx. We do this step so that we can isolate dx because we'll need it in step 3. Dx equals du over 2x. As we'll see, this is why we always end up dividing the integrand by the derivative of our choice for u. Step 3 is to rewrite the integral and remove x. We have the integral of 4x e to the u, since we substituted u for x squared, and we'll replace dx with du over 2x from step 2. Well, we still have some x's, but due to our careful choice for u and our foreknowledge that we would divide by its derivative 2x, the x's cancel out nicely. 4x over 2x is 2, so we have the integral of 2 e to the u du. Well, this is great. We don't have any x's left, and the u-Substitution method resulted in an integral that's much easier than the one we started with. That's the point of u-Substitution. Make a choice for u that results in a simpler integral in terms of u. So we can pull the constant 2 out of the integral and get 2 times the integral of e to the u du. Step 4 is to integrate with respect to u. The integral of e to the u du is e to the u plus c. This is a definitive property of the exponential function. So we have 2 e to the u plus c. Good work, but we're not done. Step 5 is to replace u with our chosen x function, which was x squared. So we end up with 2e to the x squared plus c. And that's our integral, the answer to our original integration problem. It's easy to check our work by taking the derivative of the integral, which I'll do at full speed using the chain rule. Since the derivative with respect to u of k e to the u is k e to the u, that's the same definitive property of the exponential function, but in reverse. The derivative of 2e to the x squared is 2e to the x squared, and by the chain rule we need to multiply by the derivative of x squared, which is 2x, and the derivative of the constant c is 0. So we end up with 4x e to the x squared. In review, we integrated 4x e to the x squared using u-Substitution. Then to check our work, we took the derivative of the integral and got back 4x e to the x squared that we started with. So we have confidence that our integral was correct. You can think of u-Substitution as applying the chain rule for derivatives in reverse. The last major topic we'll cover for integration is the technique called integration by parts. Again, the big idea is that we're going to replace an integral that's hard to integrate with one that's easier to integrate. You can think of integration by parts as applying the product rule for derivatives in reverse. As a reminder, here's the product rule for derivatives. By calculus convention, the function names u and v are almost universally used to illustrate integration by parts. I'm not exactly sure why, but I'll adopt the convention so we're exposed to the norm and it's familiar when you see it elsewhere. I'm also using a common shorthand where the letters u and v represent functions of x, u of x and v of x. And as you might expect, u prime and v prime represent their derivatives with respect to x. It's just a concise way to write equations involving functions without having to write a bunch of parenthesis x's and dx's. Much simpler. This shorthand works great as long as it's clear that the equations are about functions and not about variables. So the derivative of the product of the two functions u and v is uv prime plus vu prime, or as you might remember, the first times the derivative of the second plus the second times the derivative of the first. We're going to manipulate this equation a bit to illustrate the equation behind the integration by parts technique. First, let's take the antiderivative of both sides with respect to x. This gives us functions u times v on the left side, because taking the antiderivative undoes the derivative operation. We have uv prime, and we'll take its integral with respect to x, and the same with vu prime. So we've taken the integral of both sides of the product rule, and everything is balanced. Let's look at this expression, v prime times dx. V prime, remember, is dv by dx, and dv by dx times dx is just dv. And on the other side, u prime is du by dx. Dx cancels again, and we end up with du. So by integrating the product rule equation, we can get, for the functions u and v, u times v equals the integral of u dv plus the integral of v du. It's usually written to isolate the integral of u dv, so this is the integration by parts formula. And we end up with a product of two functions, u times v, minus a different integral. And ideally, the integrand we end up with, v du, will be easier to integrate than the one we started with, u dv. That's what we're striving for. Let me show you a popular example that's often used when illustrating the integration by parts technique. Let's find the integral of x e to the x dx. U-substitution won't help because our only choice for u is x, and that would give us the integral of u e to the u du, which is the same integral. So we'll try integration by parts. The first step is to choose functions for u and dv. In this example, our integrand is a product of two functions, x and e to the x. So we need to choose one to be u, and the other will be dv. There's a mnemonic to help make the choice, liate, L-I-A-T-E. The 5 letters represent 5 function types in a special order. Logarithms, inverse trig functions, which I'm afraid I don't address in this video. It's already so long and I just couldn't cover everything. After inverse trig functions comes algebraic functions, which you can think of as polynomials. In fact, there's a version of the mnemonic called lipti, where the P stands for polynomial. Same thing. Finally, trig functions and exponentials. Essentially, the list shows the most difficult function types to integrate at the top, and the easiest to integrate at the bottom. This is useful because when you look at the integration by parts equation, the function we choose for dv will need to be integrated so that we have an expression for v. This is because the right-hand side of the integration by parts equation includes v. In fact, it's there twice. And the function we choose for u will need to be differentiated because we'll need du here. So, the liate mnemonic suggests which choices for u and dv you might try first. Whichever function is lowest on the list is a strong choice for dv since it's easiest to integrate. And the object of the integration by parts method is to get an easier integral than the one we started with. So let's get back to our problem. We're on step 1, choose u and dv. We'll use liate and choose the dv that's easiest to integrate. Our integrand is x e to the x. We have a polynomial, x, and an exponential, e to the x. The exponential is the lowest on the list, so we'll let dv equal e to the x. Whichever function we choose for dv also gets the differential dx, so dv is e to the x dx, and that leaves u equals x. The next step is to find du and v, because they're referenced in the right-hand side of the integration by parts formula. I think of a 2x2 grid or checklist that has the two functions from the original integral that we chose as u and dv. So now we need du and v. We'll find du by differentiating u, and we'll find v by integrating dv. That should be easy. Using liate, we intentionally chose dv to be easy to integrate. Since u equals x, du must be dx. And dv is e to the x dx, so v is its integral. Well, yes, we certainly chose an easy integral. The integral of e to the x is e to the x, and that's v. We'll include the constant of integration plus c at the end of the problem. We won't keep track of it here. The last step is to plug everything into the integration by parts formula. U is x, v is e to the x, minus the integral of v again, it's still e to the x, and du is dx. So we've used the integration by parts technique to end up with an expression for our original integral that's easier to evaluate. That's the objective of integration by parts, to turn a harder problem into an easier problem. Since the integral of e to the x dx is just e to the x plus c, the solution to our original integral is x e to the x minus e to the x plus c, which we found using integration by parts. I'll solve another problem where the integral we come up with, the integral of v du, will in turn require another iteration of integration by parts to solve, and the integral from that expression may in turn require another iteration. The pattern can continue, but I don't want to get too far ahead. The point is, when integration by parts works for an integral, each successive integral gets simpler and simpler until we get one we can solve. You'll see what I mean in the next example. I'll try to line things up so you can see what's going on, then I'll show an easy tabular way to apply integration by parts to solving integral problems. We'll integrate x squared cosine 2x dx. Step 1. Choose u and dv. Both functions are easy to integrate, but in the Liate guide, trig functions are below polynomials, so we'll let u equal x squared and dv equal cosine 2x dx. Next, find du and v. Du is the derivative of x squared, so 2x dx. V is the integral of dv. We need to use u-Substitution to integrate cosine 2x dx, but we'll do it in our heads. The integral of the cosine of some inner term is sine of that inner term, and when we use u-Substitution, we need to divide by the derivative of that inner term. So, v equals 1/2 sine 2x. Now let's transcribe the right half of the integration by parts equation. It starts with u times v. The way we've set up our di tables, it'll come in handy later, u and v are on this diagonal. We multiply and rearrange a little to get 1/2 x squared sine 2x. Then, according to the integration by parts formula, we subtract the integral of v du. V and du are here on this horizontal line in our di table. For reasons that will become apparent in a moment, I'm not going to cancel the 1/2 and 2 just yet, or pull them out of the integral. You can do this if you like and solve the problem just fine, but I want to show you an interesting and important pattern. So the integral we subtract is 1/2 times 2 times x sine 2x dx, which is v times du here. For the sake of bringing attention to the pattern later, let me point out that when we arrange our choices for u and dv on one line, then du and v on the next, like this, that the integration by parts rule says that the integral of this product, u dv, is the integral of the product of these adjacent terms in the table. I'm using some new colors to show how the integration by parts equation corresponds to the di table. On the right side of the equation, uv is the product of this diagonal, and the integral v du is a product of these adjacent terms on the same horizontal line. Okay, as I hinted earlier, we'll need to apply the integration by parts method again to this integral. But let's take a second to point out that the first term, 1/2 x squared sine 2x, is part of the solution to our original problem, so let's not lose track of it. We'll treat the integral as a new, simpler problem. So we need to choose u and dv again for this new integral. Well, we still have a trig factor, sine 2x, and a polynomial factor, x, although the polynomial factor got simpler, from x squared to x, so we're making progress. Please, let's notice that in the pink box, we have the exact factors that contributed to this integral, v du. So, if you'll bear with me, I'm going to use those exact terms for u and dv. U equals 2x, and dv equals 1/2 sine 2x dx. I did move the dx over to dv since we'll be integrating it. Now we determine du and v. Du is 2 dx, and dv is the integral of 1/2 sine 2x. This requires u-Substitution. We'll do it in our heads again. The integral of sine 2x is negative cosine 2x, and we need to divide by the derivative of 2x, which is 2. So we have 1/2 times negative cosine 2x over 2, which is negative 1/4 cosine 2x. Now we have all four values for the second integration by parts equation, so we plug them in. U times v is this diagonal and simplifies to negative 1/2 x cosine 2x, minus the integral of v du, which is this horizontal product that simplifies to negative 1/2 cosine 2x dx. These two negatives cancel, and now we have an even simpler integral. But before we turn our attention to it, let's note that we have another part of our solution here, the uv part, negative 1/2 x cosine 2x, so we don't want to lose track of it either. The last integral is easy enough to do with u-substitution. First, let's pull the constant out of the integral. The integral of cosine 2x is sine 2x, and we need to divide by the derivative of 2x. So altogether, we get 1/4 sine 2x, and that's the last part of the solution. So we have our original problem, the integral of x squared cosine 2x dx. We applied the integration by parts method twice and came up with 3 distinct terms that will make up our solution. But we need to be very careful with our positive-negative signs because of this subtraction in the integration by parts formula. Let's step through slowly and deliberately. Then I'll show you a tabular method that will keep track for us. We began solving the problem with the integration by parts method and got this expression. The positive uv term that we noted was part of our solution minus a new simpler integral. So 1/2 x squared sine 2x. Next, we subtracted this new simpler integral, and when we used the integration by parts technique, it also had a uv term, negative 1/2 x cosine 2x. Since we're subtracting a negative, the result for our solution expression is positive 1/2 x cosine 2x. And finally, we have this last integral, and that evaluated to a positive expression. But remember, we're subtracting this entire integral, so the next to last term in our solution integral is negative 1/4 sine 2x. As with all indefinite integrals, the very last term is plus c. Don't forget. And so we've solved a moderately complex integral using integration by parts twice. Now I'm going to show you the DI method for integration by parts, which is especially helpful for problems that require multiple iterations of the integration by parts technique. It's the same math as setting up repeated integration by parts equations. It's just organized into a table for us. I kind of hinted at it with the color coding earlier, but now I'll show the full method. We start again by identifying u and dv, but we write them under columns labeled d and I. D stands for differentiate, and we'll put the value for u underneath. The I stands for integrate, and we'll put the value for dv underneath. You can still use the Liate guidelines to help you choose your candidates for u and dv. Next, write a plus sign to the left of this row, and in the next row, we haven't filled it in yet, put a negative sign. These will help us keep track of the switching signs due to that pesky subtraction in the integration by parts formula. Now, as you might expect, we differentiate the d column. The derivative of x squared is 2x, and we'll integrate the I column, 1/2 sine 2x. Now, we saw this earlier, but let me emphasize that the integration by parts formula can be read from the grid. This integral of u dv equals this product, u times v, minus this integral, v du. Horizontal products represent integrands, u dv on top, dvu directly beneath. The diagonal product is not an integral, it's just u times v. It's a tabular representation of the integration by parts formula. Since the bottom line of our table is an integral, we can repeat the steps. We differentiate the d column and get 2. We integrate the I column and get negative 1/4 cosine 2x. The positive negative sign for this integral switches back to positive, since we're now 2 layers deep subtracting integrals. The signs in the left column will alternate between plus and minus for however many times we iterate. Let's go one more time. The derivative of 2 is 0, and the integral of negative 1/4 cosine 2x is negative 1/8 sine 2x. And this line gets a negative sign. We can now read the answer to the original green integral directly from the DI table. The integral of x squared cosine 2x is equal to this diagonal product, 1/2 x squared sine 2x, minus this diagonal product. The sign is negative because we subtract the integral in the integration by parts equation. But one of the factors is negative, so when we subtract a negative, the result is positive, and we get plus 1/2 x cosine 2x. Then we add this diagonal product. We add because we're now 2 layers deep into the integration by parts formula, and the latest subtraction is already inside the one above it. There's a factor with a negative sign though, so we end up subtracting 1/4 sine 2x. We don't need to go any further. The next product would be 0 because of this 0, and with plus c, we're done. We get the same answer as when we did integration by parts, step by step. Please don't think this is a new, different, or magical way to solve integration by parts problems. All the numbers are the same. All the steps are the same. It's just that some smart person noticed that when we put the steps in a table, the results are easy to read. I mentioned at the beginning of the video that becoming proficient at calculus requires practice. I intended for this video to provide a visually engaging graphical overview of calculus and its fundamental principles and rules, and I hope it was interesting and enlightening to you. But if you're a calculus student or going to become one, you need more. In the description, I've linked to several videos by Steve Chow, whose main YouTube channel is called Black Pen Red Pen. He's the go-to source for worked-out calculus problems, and in particular, he has long-form videos where he works out 100 derivatives and 2 others where he works out 100 integrals each. They're great videos and have millions of views. You'll do yourself a favor by checking out his channels. Thank you very much for watching. We've covered a lot of material. It's almost everything you'd cover in a first-year calculus course. I hope you found this video and its style to be helpful and informative. I'm Dennis Davis. Take care and good luck with your studies.